Hello, in this video I will teach you how you can build this tennis analysis project from scratch. The project detects and tracks the players as well as the tennis balls across the whole video. We also detect the court's key points to know the player's position relative to the court, measure distances, and even determine if the ball is in or out. We will use the output of those models to know how many times a player has shot the ball and how fast he shot it. We will also be measuring the player's speed and how many meters the player covered. In addition, we'll be training two convolutional neural networks in this project. The first one will be YOlO, an object detection models to detect the fast-moving tennis balls to enhance the detection accuracy of the out-of-the-box models. The other one is a CNN that is trained to estimate the court's key points, and we'll be using PyTorch for that. So whether you're a beginner or an experienced machine learning engineer, this project will totally make your resume shine. Let's start the project. I have a project set up with one folder called input videos. This folder contains one image and one video. The image is a screenshot of a tennis match, and the video is just a small bit of the same tennis match. We are going to use those to develop and test our code. Our first task is to detect the players and the tennis ball with an object detector. We are going to use a popular object detector model called YOlO. So the way that we're going to do that is we're going to use a library called ultralytics. So we can just pip install it first. We can pip install ultralytics and then run it. It ran very fast on my machine because I have it already, but it might take a little bit more time on your end. And then we're going to create a file that is going to be called YOlO inference. This file, we're going to be playing around with YOlO a little bit. We're going to see how it works and what the output is, and see how ultralytics work. So to import YOlO, we're just going to do from ultralytics import YOlO. And to import a YOlO model, we just do a model equal YOlO and then provide what model we want. So here we want YOlO v8, which is the latest one that we can use right now. So we have YOlO v8x, which is extra large, and to run it on an image, we just do model.predict and give it the image path, which is going to be called input videos, then /image.png, which is going to be this one. We can also save it, so we can have save equal true, and that is all for it. So we can clear the output here and just run it. It's going to take a little bit time. It's going to also download the YOlO v8 model because it's not readily available on my machine. But in the next run, it will find it in my local directory, so it won't download it again. It will just download it the first time. So it's just going to take a little bit time and then run it on the image. Okay, now we're done. So you're gonna find a new folder that was created. It is called runs, and then detect, and then you have predict. If you open predict, you're gonna find the image with the detections. There are multiple detections that you can find here, which is multiple people or players, and then you're gonna have something like a tennis racket, a sports ball, which is right behind the tennis racket, so you can't actually see it. You have the clock, and you have also the name of the class, which is a person, a sports ball, whatever, and then followed by the confidence score. The confidence score is a number between 0 and 1, tells you how confident the model is that this is a person, for example. So the lower the number is, the less confident the The model is that this is going to be actually what it is, and it's not going to be a false prediction. But yeah, this is the output so far. It looks decent, and yeah, the output for one object consists of multiple things. But let's focus on the three things that we have right now, which is the bounding box, the class name, and then the confidence score. The bounding box here is consistent of mainly going to be 4 values, and it can be in multiple ways to represent it. So we have, for example, we can represent it by the x center and y center, which is the x position and the y position of the object, followed by the width and the height of the rectangle. And we can also represent it by the far ends of the rectangle, like it's called x minimum, y minimum, then x maximum, y maximum, those 2 points. We're going to stick by the x minimum, y minimum, then x maximum, y maximum format, just to stay consistent. Then we have the class name here, right here, and then we have the confidence. Yeah, we can also see those outputs in a list format, in the output format, just by creating a variable that stores the output. We just didn't store it before. And we can just print the result. And we can also print the bounding boxes, because there are bounding boxes inside the results, so we can have a look at it also. So we can have something like this, which is for box in results of 0.boxes, then print box. This is going to print the boxes. Then we're going to run it again. Going to take a little bit time. Now it's done. First, you're gonna find that the runs have another folder now, which is called predict2. Predict2 has the latest prediction that we did, and it's going to be exactly the same thing, so we won't have to look at it. So looking at the result, we have first the boxes, which is a boxes object that we're gonna look at later. Then we have the keypoints and the mask, which is not important right now. Those are not needed for detection. Those are for pose models and for segmentation. We're not going to use it here, so don't worry about them. We also have the names, which is the class names. For example, the ID 0 stands for person, the ID 1 stands for bicycle, and so on and so forth. Then we have the original image, and this is in pixels, so we don't have to worry about it. And yeah, this is all the main important stuff here. Then followed by the boxes themselves. The box themselves contains, first of all, the class. Here it's 0. 0, you can scroll up and see that 0 means person. So that's the class name, but here's the class ID, so you can map it to the class name easily. Followed by the confidence score. And then you have the isTrack, which is going to be tracking across frames in a video. We're going to tackle that when we predict on a video, so I can show you. And then we have the bounding box themselves. You can see different types of formats here. But the one that we're going to use is the XY, which is X minimum, Y minimum, X maximum, Y maximum. And here's the X position of the minimum one, then the Y position, then the maximum X, and then the maximum Y. And yeah, you're going to find that we have multiple boxes, and that is it. This is the results that we have. So in order for us to run it on a video, we can just replace the image path with the video path like this. Input video.mp4. Then we're going to run it. And it's going to take a little bit more time because a video consists of multiple images. And in that case, it consists of 214 images. So it's going to run off those images one at a time. So it's going to take a while. So I'll be back when it finishes. Okay, so now we're done. And we have a predict3 folder that we can go check out. So you can press detect, you can have the open the predict3, and then you have the output video. So let's open it, and you're gonna find a very similar output to the one that we have before. And yeah, it is just running it again and again over each frame in the video. But the one thing to note is that if you look at the sports ball, it's being detected very low. Like the number of times it's being detected in the whole video is just maybe 10. And this is going to be very hard for us to analyze the motion of the ball and how it goes and its speed and things like that. So we're going to need to fine-tune a detector model to detect the ball a little bit better so that for us to utilize this output a little bit better. So we can start by training and fine-tuning a YOlO model on the balls, on the tennis balls that are moving very fast, so that we can detect it a little bit better. So the way that we're going to do it is that maybe we're going to do another folder called training. And inside this folder, we can create a notebook. So we can call it tennis ball detector training.ipynb, and then you're going to have a notebook set up. First, before jumping in, we're gonna need to find a dataset so that we can utilize. And I already found a dataset on RoboFlow, and RoboFlow has a dataset of very similar images to the ones that we are using in our use case, where there is an aerial photo of the tennis court, and then the tennis ball is moving right here, and you also have a bounding box on it. By the way, RoboFlow also can give you the ability to create your own dataset, and it's done with very easily. But yeah, we're not gonna annotate it for us because it's already there. And you have 428 images in the training set and 578 total images. So this is not a big data set, but it's going to be good enough for us for our use case. So if you haven't already, you can just go create yourself a RoboFlow account. And then I am going to use YOLO v5 because it got me the best results in detecting the balls. So you can just click on it. Make sure that you have the show download code. And yeah, you can press continue. And it gives you the code that you're going to use to download the dataset. So you just can copy it and can come back here and basically get dataset, and you can paste it right here. So here the API key is going to be your key. I just replaced it with a string so that not to show you my key. And you can also, it also installs the RoboFlow. So we can install it right here. And I'm not going to train on this machine. I'm going to train on Google Colab. So I'm just going to add also install ultralytics. So you can install both. And you can download your dataset right here. So I want to show you the dataset that is being downloaded. I'm going to run this. Now it's being run and it's downloading the dataset for us. And yeah, we're just gonna wait a little bit for it to finish. So now it's done, And you're going to find that a new folder has been created, which is called tennis ball detections-6. If you open it, you're going to have 3 folders, which is training, testing, and validation. And inside each one, you're going to find images and labels. And if you open the images, you're going to find the images that were shown before. And if you are going to open the labels, you're going to find the class name, which is going to be, the class ID, which is going to be 0, followed by the bounding boxes that we have. So yeah, to start training, we're going to need to wrangle the dataset a little bit. It's not going to be much, but the training code requires us to have another folder inside this folder that is called the same name, tennis ball detection-6. And inside of it, we're going to have training, testing, and validation. So in order to do this, we can just do it manually right here. But I do want to make the code reproducible, so I'm going to do it with code. And I'm going to import something called shuttle that is going to help us move, copy, and paste things around using Python. So the way that we do it is that we're going to write shuttle dash move, then give it the tennis ball detection, then train, and we want to move it here. We want to move it again into another folder like this. So that way the code for the training code won't crash. It just expects it to have it in this type of format. So I'm just abiding it. So we can do the same for the test and for the validation. You can run it, and it's going to finish anytime soon. Okay, so if you see the results again, so you're going to find the tennis ball detections-6, then tennis ball detections-6, and then you're going to find the training and testing and validation folders. To train the model, it's going to be simple with ultralytics. So the way that we're going to do that is that we're just going to have write YOLO, then mention that the task is going to be detect, which is going to be detection, because it has multiple other things like keypoint extraction and segmentation. So we're going to specify that it's only detection. And we can specify the mode of it, which is going to be training. We're not going to be detecting. And we're going to specify the model itself, which is going to be YOLO v5. And I'm going to choose a big one, which is going to be this one, .pt. And I'm going to also specify the dataset path, which is going to be location slash data.yaml. And dataset.location is from your RoboFlow. You're going to find it here. So it's a dataset, and the dataset has a location attribute. So that's how you do it. And you can also specify the epochs to be as much as you want. I'm going to keep it 100. And you can also specify the image size. I'm going to specify it to be 640. And you can run it right here. Yeah, you will have the output. But I'm going to run it on Google Colab because it has free GPU. So I just moved it, just moved the code right here. The same thing, copy pasted it, and ran the same thing. It ran the model, it trained it, and then it produced another folder called runs. You open the runs, you have detect, you open detect, you have the train, and then you have multiple metrics that you can open up and see. But the ones that we're going to use is the weights. you're gonna have the best weights and the last weights. Download them both, like by pressing this download button. I already did. And yeah, you just download them, then copy them, and then paste them right here. We can create a new folder called models, and you're gonna paste it right here. So let me go paste them and come back. So I pasted them right here and renamed them to YOLO v5 best and YOLO v5 last. We're just gonna use one of them. So for me, I think the last was doing a little bit better than the best. So, but it might not be the case for you. So you can play around with both and see which one works best for you. And now we can use this model again for the inference and see how it goes. So for the inference, we can use this model by specifying its path. So we can just do models / YOLO as YOLO 5 - last.pt. And we can also specify the confidence to be 0.2. I think it's something very close to 0.2 right now, but yeah, we can run it again on the video and we can see the results. Again, this is going to take a little bit time to run on all the video, so I'll cut the video and come back when it's done. So it's done now, and we can go back to our folder, to the output folder that we have, which is going to be runs, detect, and then you have a predict 4, and you can now see that the ball is being detected way more than we had in the past. But you're going to also notice that only the ball is being detected and not the players, not anything else. That is because we only trained on tennis balls, because that was the data set. So unfortunately right here we're going to have two passes, one with YOLO v8 to detect the players and one with YOLO v5, the trained one, to detect the tennis balls. And yeah, but it's going to be doable. It's just going to take a little bit more time. If we look at the previous YOLO v8 output video, we will find that for each frame we get a list of bounding boxes. And those bounding boxes are not the same between frames as objects move from one frame to another. We want to have the ability to match the player's bounding boxes to the bounding boxes in the next frame, because right now we just have the X and Y positions of each. We have nothing that explicitly states that this is the same object between frames. This bounding box matching is called object tracking, where we say that this bounding box is the same object as this bounding box in the next frame. This way we can analyze the movement of the same players across the video. Ultralytics also gives us the ability to track instead of predict, so we can do track right here, and we can return it back to YOLO v8, and it was YOLO v8x. Run it. It's going to take a while, so again I'm going to cut the video and come back later. Okay, so now we're done. We can open it up again. We can open the runs, detect, and this time you're going to find a track. It's not going to be predict, it's going to be a track. So if you open it, you're going to find that each player has a different ID. So this is ID 1 and this is ID 2. And no matter the frame that we are in, we can always say that this one is the player 1 and this one is player 2. And this one are persons with other IDs as well. This is going to be very useful for us and very helpful for us to always say, or to always detect which is which person is which person with ease. And yeah, we can also track the balls, but since there's only one ball in the field, in in most of the times, then we don't need to track the ball. We can just detect it, and yeah, we only know that there's going to be only one, so no need for a tracker right here. Before we proceed, while we're training stuff, in the final output video, I showed you that we also are detecting the key points, multiple key points in the court. Those red key points that you see right here. Those multiple key points are going to be helpful for us to detect how much a user has covered in kilometers and how much and meters, and how much does the ball have traveled. And it can also detect whether the ball is in or out. And yeah, it is very useful for us to detect those key points. So the way that we're going to do it is that we're going to also find a dataset. And I have found a repo that does exactly the same thing, which is detecting multiple key points in the same aerial view of the tennis court. And they also provided us with a dataset. And they also have a model for it, but we're going to train our own. So the dataset right here, they have it, so you can click on it, and you can download it easily from the drive, or we can just wget it. So the way that I did it is that I used wget to download this. So you can just copy this download wget function, wget command, and we can write it on our own. So to train this, we're gonna have another notebook that is called tennis court key points training.ipynb. And we can download our dataset. And this is going to download it in a zip format. So we will need to unzip it. So we can write unzip tennis court dataset.zip. And then we can start with our code. So we can do a markdown right here and say start code. For this code, we're going to use PyTorch. So we're going to import PyTorch. And we're going to also import the dataset from PyTorch. So dataset torch.utils.data import dataset and a data loader. And we can also import the model itself, which is from Torch Vision import models, and we can also import transforms, which is going to help us transform our dataset a little bit. So you can run this, and yeah. First, we can specify the device that we're going to use. So we have device equal, and you can see that it auto-filled. So you can see Torch device, we're going to set it to CUDA if CUDA is available, which is GPU. Else we're going to put CPU. And let's run it. And afterwards, let's create our own Torch dataset. So the Torch dataset is where most of our code is going to be here. And the other things is going to be a little bit easier. So we can create a class for this dataset, which is called keypoints. dataset. We can call it whatever you want. It's going to inherit from the dataset that we imported in the Torch. So it's going to inherit a lot of the functions and things like that. And we can also plug it into our training. So the first thing is going to make an initialize function that is going to take the image directory as well as the data file. So before we proceed, I wanted to show you what data that we got by downloading our dataset. So let me move again to Colab, and you're gonna find that I here also use Colab for the training. So when you download the dataset and you extract it as well, you're gonna find that you have images. It's going to take a bit of time to open those images, because we have a lot more than 500 this time. So you're going to find the images are pretty similar to what we have and what we saw before, so nothing interesting is here. But you're going to find also a JSON file, and this JSON file has the ground truth positions of the keypoints. So first you're going to find the ID. Give it a minute, it's just acting up because it's a lot of data. So you're going to find an ID and like an ID which is the image ID, and then the key points. KPS is the key points, and you're going to find 14 of them. Those 14 are going to be X and Y positions. So actually in reality, the model is predicting 28 numbers. It's not 14 numbers. So you're going to find the X and Y positions of each one. And yeah, that is it. So given that, we can jump back to the code and create our own, continue creating our own dataset. So we can save the image directory here in the self. We can also open up the data file, which is open data file, and we're going to read the data. So it predicted this wrong, but we can import JSON because it's in JSON format, so we can just import it as a dictionary, .load, and give it F. And yeah, that is it. So in the dataset, you're going to find the dictionary that I just showed you on the Google Colab. And then we're going to write a transformation function. This one is going to standardize the image into the same size, and it's going to normalize it as well. So you can write it as transforms equal transforms, which is what we imported from Torch, and we can compose. Then we can give it a list of transformations that we want. So the first one is to transform it into a PIL image to PIL image, because then we're going to resize it to make it 224 by 224. And then we are going to make this into a tensor. And lastly, we're going to normalize it so that the values can be easier to train. The values of the pixels can be easier to train. The next function we want is to define the length of the dataset. So you can have the length of it. It's just maybe the length of the data that we have, the length of the dictionary that we read. And yeah, afterwards, we're going to create a function that is going to get an item. So in the training, we are going to get items one by one or batch by batch, and then train it on this batch and then wait for the other one to come. So the way that we're going to do this is we're going to do a function called getItem that is going to take an index and is going to return back the image and the key points. So let's start by getting the annotations of it. So we can say items.index, and then we want to get the image. So we can write image CV2. We're going to read the image, and read, and then we are going to specify the path. So the path is going to be self.image directory, then slash, then it's going to be item.id, because if you remember, we have the ID is going to be the same name as the image, and it's followed by .png. Now this will read in the image, but we don't have the CV2 imported, so we can import it using here, port CV2. And then we want to get the height and the width of the image. So we can do that easily by that. And we just can call the shape function. And CV2 reads the image in a BGR format, but we want it to be in an RGB format, so we can have it like this: CV2.CVT color from RGB to BGR. Afterwards, we want to transform the image by the transformations that we defined above. So we can have this self.transforms and give it the image. Then we want to have the key points. So the key points are going to be item, and we saw that it is in the KPS key, and yeah, this one is going to be a list, but in order for us to train it, we need to make it into a NumPy array. So we can import NumPy at the beginning, then go back here and write np.array and have it like this. And also we noticed that it was a 2D array, so we wanted to have it only 1D. So the way that we do it is we make it flatten, and flatten is just going to convert it from 1D to 2D. And at the end, we just want it to be a float. So it's an array of floats. So we can just specify the type as np.float32. Now the key points were regarding that the image has the original size, and it's not 224 by 224. So we would need to map the key points to actually show this, like to actually be mapped to the same positions after the resize. So the way that we're going to do that is we're going to do like very simple cross multiplication, where I say if where the original width was, for example, the position 240, so if I made it 224 the width, what is going to be the new location? So the way that I'm going to do it is that I'm going to multiply 224 by 240 divided by the width, and this cross multiplication will give us at the end our end position. So you can do that by specifying key points, and you can take the second so you can take the first element, then the third element, then the fifth element, so on and so forth. So you can have the width. This is how you can do it. And the way that you're going to do it is you can multiply it by 224, and then you divide it by width. And this is to adjust the x coordinates of the key points. We will need to also adjust the y coordinates. So we can start off with 1, not 0, and divide by the height and not the width. And yeah, and now we're done. So you can just return the image and the key points, and your data set is ready. So we can afterwards we can specify the we can initialize this data set. We can specify the training and validation data sets. So you can do like this, data set equal key points. Let's run this. So you can have the key points dataset. You can specify the image directory, which is images. And then you can specify the JSON file, which is going to be data slash, and this JSON file, of course, has the annotations. So it's train.json. And if you have any doubts about those locations, you can just go back here and see it. You can see that the data has images, and we have a training JSON and a validation JSON. And this is the training dataset. So you can also have the validation dataset by doing this and specifying here the val JSON. And yeah, now you have your own datasets. Just to use them in the training, we need to put them into a loader. So you're gonna do that by writing it like this, and you can specify the data loader, give it the training data set, specify the batch size. We can specify it as 8 here, and we can also shuffle. The same thing that we did for training, we can do for validation. And yeah, and now we're ready. So now we want to, now our data set is ready. We want to create our model. So to create our model, we just need, so to create our model, we're going to initialize it first. So we're going to say that it's going to be models, and we're going to choose ResNet 50, and we're going to choose the pre-trained equal true. Now, this is going to use and download a pre-trained convolutional neural network that was trained on other images, and this is going to download the model and have it in the model variable. But this ResNet 50 was not trained for key point extraction, so we will need to replace the last layer to reflect our own needs. So this is called like fine-tuning, where you get the ResNet 50, which is a trained model, and you utilize most of its layers, again, that was trained on another dataset, on this problem. So the way that we're going to do it is that we're going to specify the last layer, which is the fully connected layer, the last one. And we're going to say that this layer is going to be a linear layer, which is just going to be a flat layer with just the features, the input features, the features that is going to be inputted here, and the output is going to be 14 times 2. We will have 14 key points, and each key point has an x and y, which is going to be 28 at the end. So this just replaces the last layer of the neural network. So now our model is done. The next thing is that we want to move the model to the correct device. So whether we have this device is in CUDA or CPU, we want to move this to CUDA or CPU. And the last step is actually training the model. So we can start training the model. So first thing is that we want to define a loss function. And since this is going to be a regression function, then we're going to use a mean squared error loss. So we're going to have the criterion set to torch MSE loss. Then we're going to specify also the optimizer. And you can specify the optimizer to be whatever you want. I chose Adam, and I am going to also choose a learning rate of 1e-4. Now we can have as much epochs as we want, so I'm going to choose only 20, and we're going to loop over each epoch in range epochs, and I am going to get the image and key points. Again, I'm not running it locally because I'm going to run it on the Google Colab, but the rest of the tutorial I'm going to be running locally so that you can see things step by step. You can just say enumerate, which is going to return the index, and we can have the train loader. And yeah, the train loader is going to return back the image and the key points. So we are going to have the, it's images, it's multiple images. So you can have it, the images to device, we can move it to the device. We can also move the key points to the device that we want. We then want to flush out the optimizer so that it has, like to flush out the gradients. And then we want to predict the model, the output, like we want to use the model to predict the key points on the images that is provided. And after we predict it, we want to calculate the loss, which is going to be like this. We give it the outputs and we give it the key points, and it's going to use the mean squared error loss to calculate our loss. And at the end, we want to do a backward propagation, and we want to take a step, an optimizer step, just to do a learning step. And yeah, and just for logging purposes, we can log every 10 steps, which is going to be like this, which is if I is divisible by 10, then we're gonna print out the epoch, we're gonna print out the I, and we're also going to print out the loss. So you can go ahead in your Google Colab, or if you want to train it locally, and run it. So you can see that it ran and the loss was very high. Now it's decreasing little by little. And at the end of the day, you're going to need to save it. So after you run it, you'll need to save it in and download it. So to save it, we're just going to run torch.save, then give it the model dot state dict, and you can specify the output path of it. So you can have the keypoints model.pth, and you run it and save it. So I'm running it in Colab, so you can save it and then you can download it like we downloaded the YOLO model, and then you can come paste it again in the models directory and paste it. Now we have the other model ready. So now that we're done and our model's ready to be utilized, we can close down all this. We can save it. You can close all this up, and now we can start coding our tennis analyzer. So we can just specify the main and write it right here. And we can have the main function. And we can do a print world right now. And then we can call the main. So after we set up the main.py, we just want to start with the basically reading the video, because we won't be able to, we don't want to run it like that. We basically want to run it like frame by frame. So yeah, we're going to need to read in the video as frames and then have the ability to also save it as frames. So let's start with that. We can create a new folder called utils. And inside the utils, we're going to need to create a file called video utils. Okay. Inside the video utils, we're going to import CV2, because this is the way that we're going to read and save our videos. We're going to create a function called read video. It takes a video path, and then it opens it opens a connection to the video. And right now we have an empty list with frames, and we loop, and we're going to loop over this till the frames are done. So what we do is that we use cap.read to read in the frame, and then we have the return. This return is going to be false when there is no more frames to read. So if it is actually false, we're going to break this loop. Otherwise, we're going to append the frame to the list of frames, and then at the end of the day, we're going to release it and return back the frames. We are also going to want to have a way to save the video so that we can see what we do. So we can define save video that takes in output video frames, and it takes in an output video path, and it's going to save this as it's going to save this as a video. So yeah, I'm going to utilize what GitHub Copilot has suggested, but I'm going to edit it a little bit. So first, what the format that we want is going to be MJPG. And we want to output it as a 24 frames per second. And yeah, that is it. I'm just going to remove that as print. And yeah, this is it. In order to expose those functions to the outside, to outside of this folder, we need to create a new file called init.py. Whoops, I just need to replace this with a dot. And in the init.py, we just mention all the functions that we want to have available outside the util. So what functions we want to expose outside the utils, and we write it here. So we can write from video utils, we can import read video and save video. And after we read and save video, we can go right here, right from utils, import read video and save video. We can also put it in brackets, and because we're going to have a lot more functions in the utils, so make it neat and organized from now. And yeah, we can then read in the dataset, read in the video, sorry. So we can specify the input video path. Input video path is equal to inputvideos.inputvideo.mp4. Then we can read in the video frames by using the function that we have from the utils. And afterwards, we want to save the video. So we can create a folder called output videos that is going to have our output inside of it. So we can have the save video function that we also have in the utils. You can give it the video frames, and you can also give it the output path. So yeah, let's run this and see if it works. So there is an issue with the output format, so let me go and check it real quick. So yeah, this issue was because I wrote .mp4 at the end and it should be .avi. So if we run it again, you shouldn't get this error. And yeah, so you can open it up here in the output videos, and you're gonna see the same video again outputted to us. Okay, that's a setup. That is all set now. So we can start defining our trackers basically. So you can create a new folder called trackers. Inside of it, you can create a file called player tracker.py. And inside this player tracker, we're going to create the tracking for the players. So we're going to import YOlO. So from ultralytics, import YOlO. And we're going to specify the class, which is player tracker. We're going to specify the init function. And it's going to take in the model path, which is what model are we going to use. And yeah, and we can just do self.model equal YOLO model path. And to detect on a frame, we can use the same code that we did earlier. So we can have define detect frame, and we can just do the same code that we have earlier. So we're going to take a frame, which is basically an image. We have the results from it, and then we run the model on it. So model.track, because we want the players to be tracked here, and we give it the frame, and we also tell it to the persist function, we're going to give it true. Now persist here tells the model that the tracks that this is not going to be just one individual frame. I'm going to give you another frame afterwards, and you should be able to persist the tracks within those frames. Because we're not giving the whole video at one time, so we need to set this up so that it can remember the tracks that were done before. Then we're just going to need to have this map of lists, like this map of IDs to names. So it is in the results, so you can have the results dot names, and it will give you the results. We're going to have the output in a dictionary, where the key is going to be the player ID, and the output is going to be the bounding box. And we're going to loop over each bounding box in the results, and we want to only choose the bounding box that are people, that have a person inside of it. We want to exclude clocks, we want to exclude brackets, we want to exclude everything except people. And we're going to have another tracker for the balls, so we will exclude that also here. So yeah, we are going to take in the 0th option because it's only one image, and we're going to run results of boxes, and we are going to get the track ID, and this is the number that you saw on top of the people in the track example that I gave you before. We're going to make it as an integer. Then we're going to take box .id.toList, and this is the tracker ID. We want to also have the bounding box, so we can also do result, which is one result. We can say that the box, and we wanted to have it in the XY format, which is X minimum, Y minimum, XY maximum, Y maximum, and we're going to keep that consistent throughout this video. And we also want to have the object class name, so the class ID. So we can say object CLS ID as box dot CLS and dot toList. If I can write list correctly. And we can also have the 0th one. And we want to map this ID to the name so that we know what we're looking at. So we can have the object class name as ID to name of object ID. And we can simply say if the object name is equal to person, then we are going to take it. We're going to have the track ID and then put the value, the key as the track ID and the value as the bounding box. And if it's not a person, then we're not going to do anything. We're not going to take this. So we are going at the end to return this and have and get the results of one frame. We want to also create a function that detects on multiple frames. So we can have detect frames, and this is going to have the self, and it's going to take frames. It's also going to have it's going to utilize the detect frame function. So what we do is we have the player detections, and for frame in frames, and we want to do this. We want to detect each frame and then put it right here and append it to the output list. And now we are done. So you can have this player tracker ready for use, and it will return back the list of detections for each frame. And to also expose it outside this folder, we need to have the init one, init file, And you can write from player tracker import player tracker. You can put a dot right here. So afterwards we can detect from, we can import it. So from trackers import player tracker. So we can initialize the player tracker first. So we can have the player tracker as player tracker, and we give it the YOLO v8x1 as the model path. And yeah, now we initialized it, so let's use it to get the detections. So player detections is equal to player.detect frames, and we give it the video frames, and that should be it. So here we are reading the video, read video, and here we are detecting players. Okay, so now we're ready. But the video won't have the detections on top of it, so we will need to create a function that draws the bounding boxes on top of the video frames. So the way that we're going to do that is that we're going to add a new function into the player's tracker that is going to add those drawings on top of the frames. So you can go back again to the player tracker, then go back here, whoops, and you can have a function called define draw boxes, BB boxes, bounding boxes. So it takes in the video frames and it takes in the player detections. So we are also going to have the output frames as an empty list. Let's call it output video frames. And I am going to loop over the frame and the output dictionary. So we can have the frame, then player dict in zip, and give it the video frames and the player detections. Zip allows us to loop over two lists at the same time so that we don't have to keep an index of them. And then we just want to draw the bounding boxes. So here we are going to draw the bounding boxes. So we are going to loop over each track ID and BB box in the player dict items. And let's import CV2 and see how it goes. So the first thing, we extract the x1, y1, x2, y2 from the bounding box. And then we draw a rectangle that has the the corners of it, which is going to be x1, y1, and the other corner is going to be x2, y2. And we are going to specify a color, and we can make this color right here. So this is in an RGB format. Yeah. And yeah, the 2 here means that it's not going to be filled, it's just going to be the outside borders of it. We also want to put in some text that tells us this is the player and what ID is it. So we can just do something like this, CV2, and then put text. We give it the frame, and then we give it the string that we want to print out. So we have the player ID, and then we want to put in the track ID. We also want to have the position of it. So the position is going to be int of the BB box of 0, which is going to be the minimum. And it's also going to be the int of the BB box of 1, which is going to be the minimum y. So this is minimum x and this is minimum y. And we want to also have a little bit of a buffer. So let's do it like -10. And yeah, we can also specify the font of it and the font size and the color of it as well. So we can have this, and let's increase the size a little bit, so to 0.9. And this should be it. So and yeah, you can also assign it right here, like this one. You can assign it frame equals frame, but it actually writes on top of the frame, so we don't have to do it. So we can do this like this, and afterwards we just output this again as a frame, like append it to the output, and then at the end of the function we return the output frames. So yeah, let's also return back to the main. Use the player tracker right here. So we are going to be drawing some things. So draw output. And the first thing that we are going to draw is draw player bounding boxes. And we are going to draw the bounding boxes, give it the video frames, and give it the player detections. The video frames right here, we are going to, we can call it here the output video frames. And then save it again. So yeah, let's run it. There's an error. Trackers dot no modules is called like that. So trackers dot player tracker. Whoops, I misspelled it right here. So it's tracker. You can clear the output and run it again. So it is going to take a while to run this all. So yeah, I am going next to create a stub where we can save the output of this tracker into a file and then read it instead of predicting it again and again. And it will help us in development. It will help speed up the development a little bit. But yeah, this is going to be the next step. So yeah, I'm going to cut the video for now and come back when the run is over. So I've come into an error right here, and it seems to be that I have missed a bracket. So if you did the same mistake, just come here at the bracket for the int and make sure that your brackets are correct. And yeah, I think I'm missing one. So yeah, right here. And so everything is good now. So yeah, you can run it again. And yeah, I'll come back when it's done running. Okay, so now it's done. So let's go back to our output videos and open this. And you're going to find the output very similar to what we had in our ultralytics output, which is going to be the player and then the ID. I didn't put the confidence because I don't care about it right now. I just care about the IDs and the bounding boxes. So it all looks good now. I just want to add another thing in the player trackers, which is going to be basically saving the output so that we don't have, each time when we run, we don't have to run the detector again. We can just take the output if there is any. So we can create a folder called tracker stubs, like this. Whoops. And we are going to be saving the output of this detect frames in a pickle format. So let's import pickle. And right here in the detect frames function, we can take two more inputs, which is going to be read from stub. It's going to be either true or false. If it's false, then we're going to run it. If it's true, then we're gonna put it into a stub. Then we are going to take a stub path. And this stub path is going to be none as default. So yeah, if we have the stub path, then if we have the stub path, which is going to be if stub path is not none, then we are going to save it, basically. So we are going to open it and then pickle dump the player detection inside this path. We are also going to check if the read from stub is actually true, and if it is, we are going to read the stub and not basically detect each frame. So we are going to check if read from stub is true, and the stub path is not equal to none. Then we are going to open it, then load the pickle, and then return the player detections. And yeah, this is it. Right now, we want to add those two in. So in the detect frames, we are going to give it two more things. We are going to read from stub is equal to false right now. We're going to make it false because we don't have a stub, and we're going to generate it after this. And the other one is going to be stub path, and we are going to tracker specify the output one. So specify the output path, which is going to be tracker stubs slash then player detections dot pkl, which is the pickle format, pickle extension. So right now we're going to run it again, and it is going to detect the frames, but afterwards it's going to save it in the stubs so that we don't have to run it again. So let's run it, and we're gonna have to wait a while. So I'm gonna cut the video again, but hopefully this is the last time that we're going to detect it with the players. So we're gonna do another one with the balls, but we're also going to run it one time, and then the runs should be a little bit faster afterwards. So yeah, see you then. Okay, so now it's done. And you can find that in the tracker stubs, you can find the player detections.pickle. So all we do right now is just change this to true. And if we run it again, then you are going to find that it takes way less time. So give it just a couple of seconds and it's done. So you can go also to the output folder, and every time it overwrites the file, and you can see that we have the same output. Now we want to do the same thing, like we want to track the ball. So you can copy it, then copy the player tracker, and then you can paste it right in. After pasting it, you can rename it to a ball tracker, like that. And after you rename the ball tracker, you can rename also the class name. And we're going to change the detect frame a little bit. So the detect frame right here basically is checking for the if class name is equal to person. And since that we have only one class, then we can delete this if function. So we can delete this if statement. And we can also delete this checking for the names. And we can also delete this because it's not used anymore. And yeah, we can rename the player dict to ball dict. And let's also have it right here and right here. And let's not track it since we only have one ball, so we can just predict it. We can set the confidence to 0.15. I think that is that was good enough, and 0.2 is also working fine. So we're not gonna have any tracks, so we're gonna have only one ball. But we want to have the output consistent, so we're gonna have just one, which is track 1, and put at it the result. And yeah, we also want to have the detect frames to stay the same, but we don't want to have it to be called player detections. We can call it ball detections and rename each instance of this. And now we're done. So the last thing that we are going to need to change is the draw boxes. So the draw boxes right here is going to be ball ID, and we can also call it here ball dict. I don't think that we're gonna change anything else than the naming, but yeah, that is it. Yeah, if I didn't miss anything, I think this is it for this is it for this class. So we can go here. We can also import it in the player tracker. We can import ball tracker. We can go back here and we can import ball tracker as well. Let's so yeah, let's detect now the balls. So we can call detect players and ball. We can also have a ball tracker, which is going to be ball tracker. And we are going to give it this time the model path to be models and YOLO 5 dash slash last dot pt. And we are going to detect also the frames. So like we did in the players, we're going to do with the ball as well. So we're going to call it ball detections. We are going to read from the stub if it exists. If it doesn't, then we read it. Then we have the We can call it the ball detections and save it as well. And yeah, afterwards in the drawing the outputs, we can also draw the ball output like this and give it the ball detections. And yeah, that should be it. We can now run it. We'll have to wait a little bit for the ball tracker to run the first time. But yeah, I'll come back when it's finished. Yeah, before I run into an error that tells me that this doesn't exist. So you can change it to read stop from false till we have the first initial stub. So I'm running into another error again. So let me figure it out and come back to you afterwards. So I'm back and I have this persist equal true. This is for only tracking. So make sure to remove it and save it again and run it. And hopefully this time it won't crash again. Just give it a minute, make sure that it's running, and then I'm going to cut the video if it is. Yeah, it is running. So I'm going to come back when it's finished. So yeah, see you then. So now it's finished and we can go back again to the output video, now see it. And you can see that the ball is being tracked as well. So let's give the ball another color than red so that we can differentiate it quite easily. And we can do this by going to the ball trackers, then go to draw boxes and give it here in the RGB section. You can just give it another color. And I am going to choose a yellowish color like this. And this time I'm going to use the stubs so that I don't have to run it again. So like this, and you can just run it again. And yeah, this time it should be a very fast run, so I'm not gonna cut the video. Yeah, it's done already. So you can now see the results. The ball is in yellow. You can also change the writing to be yellow. So like here, you can also change it to be yellow. And yeah, that is it. Let's now detect the court key points. So in order to do that, let's also create another folder that is going to be called court line detector. And we are going to have a file inside of it that is called court line detector.py. So this is going to read in the model that we have trained and then use it for prediction. So in order to do that, we are going to import Torch, because the model is written in Torch, and we are also going to import Torch vision, and we are going to specifically import from it the transforms to apply the same transformations that we did earlier on this on the images. We are going to also import CV2 to read in the images if we want, and to do any any manipulations if we want. And yeah, let's start writing the class. So we can have the we can write the court line detector, and we can start off with the init function. And we are going to take the model path as an input also. So let me just fix that. And you can have the self model equal models dot. We're gonna do the same one. So we're gonna have the models.resnet, and I did not import it, so I need to import it first. And we are also going to replace the last fully connected layer with the one that that is going to have the 28 key points. So fc is equal to torch dot nn dot linear, and then it's going to be self dot model dot fully connected in features, and then have the 14 times 2. We can just write 28 if we want, but I just write this to remind myself that it's 14 key points and with X and Y. Then to load in the model, I'm just going to do the self.model.load state dict. We are going to load in the model, and I am going to map it to the CPU, because right now I have a CPU machine and I don't have a GPU inside of it. So I'm just going to map it to a CPU. So now we have created the model, and we have loaded the weights of the model inside this model so that we can have the same output that we like we can get the predictions of the trained model that we have. The last thing that we are going to do in the init is going to specify the transform function, which is going to be the same thing that we did. So you can actually go copy and paste it. So you can have it right here. If you have it ready, you can just copy paste it if you want, like this, and it should be fine. Then we are going to create the predict function. It's going to take in the image, which is a frame. We are going to basically predict the first image and not predict it again, because the camera is not moving, so the key points won't change positions. So we are just going to run it on the first frame, and that's it. So what we do is that we have the image. We just make sure that it's in RGB. So we can just convert it from BGR to RGB. And then we apply the transformations on the image. So we just do the self.transform and then give it the image RGB. And we want it to have like we want to unsqueeze it. And yeah, we then want to run the model on it, and the way that we do that is that we do it like this: outputs equals self dot model, and then give it the image tensor. And you have the key points right now in the outputs, so you can have the outputs dot squeeze, then to list. By the way, unsqueeze right here just means that if you have the image like this, you just put another list on top of it. So it's going to be like this. This is unsqueeze. This is essential because when a model tries to predict things, it usually takes in a list of things to predict on. And if you are just predicting on one thing, like this one image, you need to put it into a list. And the output is also going to be a list. So we also want to have the zeroth, like you want to have the 0 position of it. You can just write do 0, or you just can squeeze it, and by squeezing it, it just removes the list. So back to the key points thing, where we squeezed it. We can move it to CPU, and then we can make it into a NumPy, like this. And we can also have the like the key points right now are the positions for the 224 by 224. So we need to map it again to the original image size and image width. So the way that we're going to do that is that we're going to have the original height and original width, and we can leave it like this, or we can just take the first two and do it like that. So the way that we did it when training is that we did it with cross multiplication, and this is how we are going to do it again right here. So we are going to get the key points, then get all the width of the key points, so every other element starting from 0. Then we are going to multiply it by original.height over 244.0. This is going to map it to the original width and the original height. We are also going to do the same thing, but for the heights. This was for the width and this one was for the heights. This one starts from 0 and this one is going to start from 1. Every second element starting from 1. And yeah, this should be it. We can just return the key points, and there you go. That is how you get the results from the model. Before returning back to the main, we also want to draw those predictions on top of frames. So let's do that while we're here. So we can just have the define and called draw key points, and we can take an image and the key points that we have just returned. We can loop over each key point that we have, and we want to loop over 2 by 2. And this is because it is going to be xy, then xy, then xy, and one xy is one position. So we are going to loop over it from 0 and till the length of key points, but the next step is going to jump 2. So instead of I being 1, it's going to be 2. So we're going to skip 1 in the middle. So we're going to make x equal int. We just make sure that it's an int because like when you specify a pixel position, it must be an int, and it won't be fractions. It won't accept any fractions. And then it's going to be the ith position, and the y is going to be the I plus 1 position. Afterwards, we just want to display two things. We just want to put the dot in the place, and then we want to have the key point number on top of it. So you can have the cv2.put text, and you can write it on top of the image. Then you can write you can write the str and then I divided by 2, and this is integer division, so it's going to be an integer at the end, and x were minus 10. So this is going to take the x position of it and the y position, and we're going to make a buffer 10, so we can put it on top of the point. So we are also going to specify the font and the font size as well. So let's do that here. So font, we also going to choose the simplex one. We are going to choose font size. Then we are also going to choose the color. This is in a BGR format, so this is R, which is red. And then we are going to specify this. And at the end, we want to put a circle on the image in the XY position. And its radius is going to be 5 pixels. And we are also going to make it red. And then we are going to specify that it's going to be filled. So -1 means that it's going to be filled. And at the end of the day, we are going to return this image. Now we are done with drawing on one image, but we also want to have a convenient function where we can take a list of images, which is all the video frames, and run all and draw on all of them and return back the results. So we can have the draw key points again, but on video, and this takes in the video frames, then the key points, and it has the output video frames, and yeah, it loops over the video frames and the key points. Actually it did it like the autocomplete did it wrong. So you can remove this because there is only one set of key points and we're gonna draw it again and again. So the key points right here, and we are going to put it right here in the key points. So again, always check what GitHub Copilot is suggesting, because it might suggest things that are wrong and you need to fix it. So draw key points right here is, I think, is working fine. The draw key points, it takes key points and then the frame. I'm just checking it again. So yeah, it looks like it's working fine. So yeah. So before moving forward, we just want to create an init file. And we want to expose the chord line detector again outside of this folder, so we can use it in the main function, in the main.py. So we can write .from chord line detector, import chord line detector. We also want to have, we want to do the same that we did with the trackers. We want to initialize it, then detect on the frame. So we can do that by writing here chord line detector model. We can chord model path. We can specify its path first, which is models dash chord line model.pt. Not sure that it's the correct name, so I'm going to, yeah, it's not. So just copy the name and paste it right here. Then initialize the chord line detector like this. And at the end of the day, get the chord key points. And we are going to run it like this, .predict, and give it the first video frame. So give it only one video frame. And it should return back the key points. And after that is done, we can also draw it. So to draw it, we can just write it right here. So you can have it right here output video frames, and you are going to do court line detector dot draw key points on video, and then give it the output frames right here. Give it the output frames, and then give it the court key points. So we have the court key points right here. Just give it right here, and you should have the output ready. I think this might not. Yeah, I misspelled it. I misspelled it at the beginning, so I'm going to fix it. I also noticed that here I'm detecting both on video frames. I should be detecting on output video frames. And yeah, that should be it. I'm making sure that here we're reading from stubs. And this prediction shouldn't take long since we are predicting on only one frame. So yeah, let's try it out. Okay, so now it's done. So we can go back to the output video right here. And we can see that the key points are being extracted correctly. There is a little bit of error. If you notice, like for 3, it's a little bit shifted to the right. Things like that. But it is close enough for our use case. So we'll proceed from here. Yeah. So let's return back to the code. And let's close down all those unnecessary tabs. Let's return back to the output and focus more on the ball detections. So you can see that the ball is being detected way better than what we had originally. But for example, you can see right here the ball is not being detected at all. And it's being detected like the one frame before and the one frame after. So like this and this, like you can see, like we can easily estimate the position given the position before it was lost and the position after it was lost, like this one. We can estimate it to be, for example, the middle position. And if there were more than one position, you can divide it by 2, divide the position by 2, and to estimate it. Luckily, we can just use the interpolate function in the pandas library, and it would fill out those balls for us. So let's create that now. So we can go back again to the tracker, which is the ball tracker, and we can write an interpolation function. So let's start here. So we can just write here, define interpolate ball positions, and it's going to take in the ball positions or ball. Yeah, we have it called ball detections in the main, so but we don't care about that right now. So what we do is that we only have one track, so we don't actually need to have the track number. I just need the list of positions that we the bounding boxes that we get. So I can just have the ball positions equal, and then dot get 1, and if there is none, and if there is no 1, that means that there was no detections. I'm just going to return back an empty list. And I'm just going to do a one-line for loop that is going to loop over the ball position. So now we just have a list of bounding boxes that is going to be empty when there is no detections. The list inside is going to be empty when there is no detections. We can convert this list into a data frame so that we can do the interpolation quite easily. So we can import pandas as PD. Then we can just do PD dot data frame, and then give it the ball positions, which is this list, and also give it the columns, which is going to be the column names. It's going to be x1, then y1, then x2, y2. And I'm going to put it in a df ball, positions, data frame. This is what it's called. And then this just convert the list into a pandas data frame. Then we just interpolate the missing values. And the way that we do that is that we use the interpolate function inside of pandas. So we can just do this and run interpolate. And this interpolates if something is missing between two frames or between multiple frames, but it's not going to interpolate positions at the beginning. So at the beginning, we want to make sure that there is no missing values, not to crash our code. So we can just duplicate the earliest detection. We can duplicate it to the start of the frames. So the way that we do it is just we backfill it. So we do the bfill function to do it. Again, this is just to handle the edge cases of not getting any detections the first frame, but otherwise it should be fine. And then at the end, we just want to convert this back into the same format that we got the ball detections from. So we have ball positions equal, and then we can start it again. We had 1 as in the track ID 1. And then we can put x, which is going to be from the for loop, the one-line for loop that we're going to have, in df ball positions dot to numpy. I'm going to make it a numpy array, and then I'm going to make it into a list. And this is going to return back a list of dictionary where 1 is going to be the track ID and x is going to be the bounding box. It is the same format that was handed to this function. So I'm just going to return it back to the ball positions. And the reason that we changed it to pandas data frame then back is that we just wanted to use those interpolate function in the pandas data frame so that we don't have to do it by hand. Yeah, so now we can just, here, we can just do it like this, and we can call the interpolate function. So we can have the ball detections. We can call the ball detections, and it's called the ball tracker. So ball tracker dot interpolate ball positions and give it the ball detections. And yeah, we can run it again right now and see how it goes. Okay, so let's open this again, and you're gonna find the ball is being detected way more. So So you, like the last example I showed you, here the ball was not being detected, but now it is being detected. Although you can find here that the bounding box is not completely on top of the ball, but it is close enough. So it is close enough, and if I run the whole video, you're gonna find that the ball is being detected in almost every frame. This is going to help us way more in the analysis and makes it more smoother. So yeah, so we're gonna keep that. And after we, before we continue, I wanted to add the frame numbers on top of the frame so that we can start and trace back how it functions. So we can just write draw frame number on top on the top left corner. So we just want to have the frame number on the top left corner of the video. And we can do it like this. I am going to explain the code that was written by the GitHub Copilot, which is going to be looping over each frame, then putting the frame and then the number of the frame, and then it's specifying an exact position of it, which is a X position of 10 and a Y position of 30, and it's going to specify also the font type and the font size and the color. So yeah, we can also make the color like this. But yeah, we should have the frame number on the top left corner of the video right now. So let's run it again. Okay, now it's done. So let's open it, and you have the frames on the top left corner, like you see here. I'm just going to minimize this a little bit so you can see the frame number, and it's incrementing. We can now utilize it. We'll be able to utilize it further on when we're tracing back anything that is buggy that is happening. But yeah, it's going to be super useful here. So let's see the output again. And when you see the output, we have a lot of people being detected, and we just want to detect the 2 players in the field. We can do that by selecting the players closest to the court, and we can use the key points to determine which players or people are closest to the court. So let's do that right now. So we can return back to the main.py, and we can see that we have the court key points and we have the player detections right here. So we can basically add a function that can determine which IDs or person IDs that are closest to the court key points. So we can go to the player tracker and add a function that is called choose and filter players. So we're going to choose the players and filter them based on their proximity with the court. So let's go back again to the trackers and the players. And let's create a function called define choose and filter players. This takes in the court key points, and then it takes in the player detections, and yeah, we are just going to choose the players based on the first frame and not all the video. So we can do that by just getting the player detections for the first frame. And we can just make it like this. We'll take the 0th elements of the player detections. And we can also do another function called like chosen players equals self dot choose players that takes in court key points and the player detections for the first frame. Now let's create this function. So we can have the define choose players self then court key points and then the player detection frames. We can start by calculating the distances. So the distances between each player and the court, and we can do it by looping over each track. So track ID, and we have the bounding box in player. Let's call that player dict. So because it's a dictionary, so we can have the items. And you have the track ID and the bounding box. And then we basically want to get the middle of the box. So we can do that by getting the x minimum, y minimum, and dividing it by 2 to get the middle position, and do the same for y. And rather than doing it here, we can also add it in the utils, because we are going to use that also elsewhere. So in the utils, you can go ahead and create another file called bbbox, which is bounding box utils.py. And basically, I want to get the center of the box, so we can have the define get center of bbbox, and then I'm going to give it the box, and I'm going to extract the xy positions, add them both, divide them by 2, and add them both, divide them by 2, and return at the end the center x and the center y. The only thing that was missed here is that they need to be int, so that they can be like pixel positions. So we can have it like this, and it should be good to go. We also, while we're here, we also want to measure distance between any two given points, so that we can measure the distance between the point and the bounding boxes and the key points. So the way that we do that is we're going to create another function that is called measure distance. It's going to take point 1 and point 2, and point 1 is xy, and point 2 is going to be xy as well. And we are going to return this equation. So this equation basically measures the distance between any two points, and it does that by treating them as a right angle rectangle and getting the hypotenuse of it. So just to visualize it, you see here that you're measuring the distance between A and C, and the way that we do that is that we get the A squared, which is the difference in the difference in y, plus the difference in x power 2, and then you get the square root of it, and this is going to be the distance between A and C. The same thing that we are doing right here, and multiply 0, like the power 0.5 is just the root. And now we just want to export those functions and the init. So you can have from dot bbbox utils import get center and measure distance. And in the players, we can also have we can also import this from the utils, and we can import system as first, and then system.path.append one folder before that, just because we want to go one folder back so that we can see the utils. And then we say from utils import we want measure distance and get center of bounding box. Now we are ready to use it, so we can say get center of bounding box and give it the bounding box. And now we have the center of the bounding box. And now we can assign it to the another variable called player center, and now we have it. Now we just want to calculate the distance between the court and the player. And we're going to calculate the distance between the player and each key point in the court and see which one is the closest. So we're going to have basically minimum distance is equal to float and then infinity. Then we are going to loop over each key point and court key points, and we're going to loop over 2 at a time because each one is going to be 1 point. Then we are going to get the court key point, which is going to be the X and Y positions. Then we are going to measure the distance between the player center and the court key point, and then put it into distance. And if the distance is less than the minimum distance, we take the minimum distance and put it here. And yeah, that is going to be it. So at the end, we have the distances dot append, and then we append 2 things. We append the track ID. Don't know if that was written correctly. Track ID, and then we append also the minimum distance. So this way we have a tuple. We have a list of tuples with a track ID and the minimum distance. So now we just want to choose the track IDs that have the lowest distances between the key points. So we can just sort them. So we can sort the distances in ascending order. Okay. And we can do that by this. So distances.sort, and then we sort by what value, 0, which is this one track ID, and 1, which is this one. So we sort the distances based on the minimum distance. And then we choose the first 2, basically. We get, actually, let's call it choose the first 2 tracks. And you can have the chosen players is equal to distance of 0 and 0, which is going to be track ID. And then we are going to get the next one, which is 1 and 0, which is going to be also track ID. So this is going to be 2 players, and we can just return back at the end the chosen players. And now let's also filter out the chosen players. So now we are going to loop over the frames, and we are only going to keep the detections related to those 2 chosen players. So I can have like filtered player detections, and I'm going to keep it as an empty list. Then I'm going to loop over the player detections, and I am going to choose to loop over each track ID in the player dict, and I am only going to take the ones that are in the chosen players. So this is a one-line for loop that can be a little bit complicated, but all it's doing is that it is looping over the player dict item by item, and if the track ID is in the chosen players like this, it is going to put the track ID in the bounding box and return back the dictionary. Afterwards, after we have the dictionary, we append it to the player detections, and then we just return back the output. So now we have the output ready, and we can go back to the main right here, and we can now filter out the required players. So we can have choose players, and we can write player detections equal player trackers dot choose and filter players. We can give it the court key points and give it the player detections, and now we have the last player detections. We should now have only 2 players and not all the other people. So let's run it and also see the output. Okay, so we can open it again, and like you see, like other people are not being drawn because we filtered the bounding boxes out, and only 2 players are being detected, and this will also simplify our lives a little bit, simplify our lives better here. So in the final output video that I've showed you, I've also showed you something like a mini court that is being drawn here. So you can see that this is the court that is being drawn here, and here's the position of the player 1, here's the position of player 2, and here's the position of the ball itself, and this is what we call mini court. I call it mini court right here. We are going to be drawing on it, and also we are going to make it very similar to the original proportions of the court, so that we can measure distances and we can measure like the distance between the player and the ball, and how much did the ball cover and how much did the player cover quite accurately. And yeah, so we are going, it's good for visualization, but it's also going to help us a little bit when we are trying to determine the distance between any 2 things. So we can start by drawing this, and then we can move on from there. So you can write tennis court dimensions, and you have here the tennis court dimensions that you see. So this is called the high one is called the double alley, which you can see it's a 10 meter. You also have the center line, the service line, the center line, and you also have this part is called no man's land. So yeah, we're going to be putting like some of those dimensions in constants, and it's going to help us understand what is the actual distance that is being covered by players in the ball. So let's create a folder called constants. And let's create inside of it an init file. And we can start by just writing down a couple of things. So we can write the single line width, which is going to be 8.23. This is what is called the single line width. I just have the 8.23, which is this one. And this is the double line width, double alley. So it's 10.97. So we can also write it here, double line width, which is going to be 10.97. There is a half court line width. Actually, it's height, and it's going to be 11.88. And let me tell you which one that I'm referring to, which is this one. This is the half court height. This is the meter in meters. You also have the service line width, and it is 6.4. You also have the double alley difference, and it is 1.37. And again, this is the double alley difference right there. So between the the single alley and the double alley, it's 1.37. Those are just a couple of contents, so like constants that are going to help us map between pixel difference and meter difference. So yeah, you can just take them from here, 5.48. And while we're here, we also want to determine the heights of the players themselves. And you can actually, if you opened it, you can see that you can see the names of those players, and you can Google their heights quite easily. And I have Googled them and I've known them, so I'm going to just write them here. So player 1 height in meters, and it's going to be 1.88. And the player 2 height in meters, it's going to be 1.91. Those are also going to help us a little bit in mapping out pixels to meters. Okay, so now we're done with the constants, and now we want to draw the mini court. So we can make another folder called mini court. And we can write the mini court class, minicourt.py, and yeah, we can import CV2, and we can also import sys, and we can we can sys.path.append, and we can also return back one folder. Then from utils, actually let's not do that right now, but we can import constants. We can import the constants. Okay, sounds good. We can define the class, start the class, which is the mini court. Then we can define the init function. And we can give it a frame. This frame is just going to be the initial frame of the video. just to get the size of it. So we can start by defining how start by defining how wide and how tall this should be, like the drawing style. Should it be large? Should it be small? I'm going to set it like the ones that you see it right here. But yeah, feel free to play around with it a little bit. So I'm going to set the self.drawing rectangle width, which is going to be 250. It's going to be 250 pixels. So this white rectangle is going to be 250 in width, and it's going to be 450 in height. And the difference between like this padding difference, this padding difference is going to be 20. I'm going to make it 20 pixels around. So it's there's going to be a little bit of padding between the court itself and the white rectangle, and there is also a little bit of a buffer between it and the top and the right. This is 50 pixels, so I'm just going to define it right here. So let's define the drawing rectangle height now. Again, this is the white rectangle that you saw, and it's going to be 450. Let's also define the buffer between which is going to be this empty one, this part and this part. The buffer between the edges is going to be 50. And the padding itself, which is inside of the white rectangle. So padding of the court is going to be 20 pixels. So yeah, so now that this is done, we will just want to determine where should we put the this rectangle. Like now we should find out the exact x and y coordinates we should put this rectangle on. So let's create this function here. So we can have define set canvas background box position, and it takes self and it takes a frame, which is going to be the first frame. Then we do a frame.frame.copy just to not override the original frame. We don't need to actually here, but let's keep it. We can define the end of the frame, which is this bit, this end bit, to be the frame.shape1, which is going to be the width of it, minus self.drawing, like buffer, which is going to be 50. So this is going to start 50, but from the end. This is the end. And we can also do it self.end_y, and it's going to be self.buffer, which is going to be 50 from the top, and then 450, which is going to be this one. So self.buffer, then self.drawing rectangle height. We also want to get the start and the end. So the start is going to be end x minus the width, and the start is going to be also the end y minus the height. And now we have the positions in the self, so we don't need to return it, but we do need to call it. So we can call set canvas background position, and we can give it the frame. Awesome. Now we just want to see the position of the court itself, this mini court. We made the position of the rectangle, the white rectangle. Now we want the position of the court. So let's also do a function for that. So define set mini court position, and it takes in self, and actually we don't need anything else. So what we do is that we're going to just add the paddings in the start and like the start x and yx. So we can have the self.court start x equals self.start x plus self.padding court. Okay, then we can do the same for the y, and we can do the same for the end x, but instead of adding it, we subtract it so that it can have a buffer right here. And we can also have the end x, like the end y, so the end y minus padding court. Now what we also want to do is that we want to define the width of the court. So the court width, and let's call it court drawing because it's just the drawing, it's going to be court end x minus the start x. Now we also need to call it like that in the init. Okay. Now we just want to specify those court key points, the ones that you see here in red. So those court key points are going to be a little bit manual, so bear with me a little bit. So we are going to write define set court drawing key points. Okay, I have misspelled this right here. It takes in nothing. It just takes in the self, and we can start by defining the key points. So we can have the key points all at drawing key points. We can have it all as 0, and we can have it 28 times. So this is going to create a list of zeros, and it's going to have 28 zeros. So let's define 0.1 or 0.0 to be specific. So 0.0 is going to be just this point right here, which is going to be the start of the court. So start x and start y. So to do that, we're just going to create drawing key points of 0 and drawing key points of 1, and it is going to be the start x and start y, and let's also put ints on top of it so that we can make sure that those can fit into pixel positions. Next, we just want to do 0.1, and and 0.1 is going to be this one, which is going to be this one. This is the end of x, but still the start of y. So you can have the drawing key points of 2, 2 and 3, like 0 and 1 is for position 0, 1, 2 and 3 is for position 1, which is going to be the end of x and the start of y. This is correct. So let's move forward, and let's also do it in the point 2. Point 2 is going to be this point, which is right here. And this is two half courts with each other. This is a half court and this is a half court. And we want to be able to make it as proportional as possible to the actual meters that we have in the constants. So we're going to be adding some conversion logic right here. So this conversion logic is just going to be cross multiplication, but since we're going to use it over and over, let me put it in the utils. So in the utils, you can have a new file called conversions. Conversions.py. And you can open it right here and define two functions, which is convert pixels to distance and convert meters to pixels. So we're going to have convert pixel to distance 2 meters. So convert pixel distance to meters. So for example, if the user moves from here to here, how many meters did he move? We have the amount of pixels he moved he moved from X and Y position, and then he went to X and Y position, but we don't have the exact meters that he moved. And we can do that by doing some cross multiplications and seeing, okay, so from this point to this point, it is X meters. So from this point or from this pixel to this pixel, it should be Y meters. We can do it with simple cross multiplication. So the way that we're going to do it is that we're going to take the pixel distance, and then we are going to take the reference height in meters, then reference height in pixels. Then we're going to return it back here. So let me explain it first. So now we have the width of this in pixels, and we also have the width of this in the constants if you open it. And yeah, the double alley line, this one, it's in meters. So you have this in pixels and meters. So you can do any cross multiplications to find anything. So for example, the height in pixels, like the width in pixels is, let's say 20, and it's in meters, it's 10.97. And now I want to give an arbitrary pixel distance, and to change it to meters, I'm going to take this, multiply it by meters, then divide it by 20. This is simple cross multiplication. And this is and we can actually do it in just one line like this. So pixel distance times meters over the pixels in heights. We also want to have the define convert meters to pixel distance. So we have also the reference height in meters and the reference height in pixels, and we're also going to do some cross multiplication, but this time we're going to multiply by the pixel distance over the height distance. And yeah, so let's now expose it right here. So from dot conversions, import convert distance pixels and convert pixel distance. And let's go back here. I think this should be constants. Why is it adding an SRE? Don't mind. Then yeah, we can add from utils. We should import convert this one, and we should also convert pixel distance to meter distance. So yeah, So let's continue down with the points. We have the drawing point, drawing key point of 4, and it is going to be the same x value as the start, so the x didn't change, so we can just write it as int self.court start x, but the y value changed, so we can have this as so position 2 is going to be so the start y plus 2 half courts. So the way that we're going to do that is we're going to take this start and then y, then add it to convert pixels, we want to convert meters to pixels, and then we have the constants dot, we want to get the half court height. I just want to remember its name. Yeah, so half court line height. So this one, and since it's going to be the full court, like from here to the net is the half court, so we want to do like 2 times this, so we're going to multiply by 2. And let's not forget to add the constants.half court, and we want to give it the 2 references that we have right now. So the reference that we are going to use is that we already have the court width. So we can simply write it right here. And this court width is going to be constants.double, let's also go remember the name. It is the double line width. So we're going to give it the double line width, and then we are going to give it the court drawing width. Okay, so now we have the point 2 ready. And we are going to basically converting a lot of this like meters to pixels a lot. So I'm going to make it a separate helper function right here. It's going to be convert meters to pixels. It's going to take the meters. And we are going to utilize this. So you have this and you run it like that. And instead of meters, instead of having it a constant, we can take it here. And now we get the distance in pixels when we have the meters. So we can just do like this. Self, and we can close down the bracket here and remove this. Now it's a little bit easier for us. Moving forward to point 3. So point 3 is going to be, again, this point, which is going to be point 2 plus the width of it. So let's do it. It's going to be drawing 6. So we're going to use the same x value as the first one, like that. And then we can, actually I forgot a t right here. Let's add it right here. We can add the core drawing width, since we already have it. And we can keep the same y value as the previous one, so that we So we can keep the same y value as this one. So we had 2, and we're going to keep the y value to have it for 3. Again, we're going to loop over it again for 0.4, and 4.4 we have another 14 points that we want to do. So what I'm going to do, to not bore you, I'm going to fill it out and then come back later. So I've filled in all the points right here, all the points, and at the end I just assign the drawing key points into a self variable so that we can have it here. So right now we're just going to do the self and going to call it again. And right now we just want to define the lines. So right here you have, apart from the points, you have the lines. So you need to understand which lines you want to collect, like which 2 points you want to connect the line with. And for this, we're going to also manually select those. And let's start with it. So we can define set court lines and then give it the self, and self.lines equal. And if you look at this, you have a line between 0 and 2 and 0 and 1. So we can put them right here. So 0 and 2, and you can also have 0 and 1. You also have a couple more, but I don't want to go I don't want to go through them all to not bore you. You can just it's pretty straightforward. So I'm just going to copy paste it, and I pasted it, and I pasted the lines right here. So again, from 0 to 2 there's a line, from 4 to 5 there's a line, and you can find that those are what we see. So you can set court lines also right like this, and that is it. And we are set with the I think there is no more manual work right here. So I think we are ready to maybe draw it. So let's draw it. So we have the draw background rectangle, which is the white rectangle that you saw. So we can take in the frame, and we can just first initialize the we want to draw a white rectangle. So we're gonna do shapes like np zeros. Let me import numpy. Okay, so now we have the same, like the frame that we had, but we like the image that we had, but with all zeros. And this is going to help us do this a little bit of transparency. You can see that it's not an actual like filled color. It has a little bit of transparency in it, and this is the way that you do it. You do a dummy image, which is going to be all zeros, and then we're going to add it to the image that is going to be the frame, but with a little bit of opacity difference. So on top of this, we can draw the rectangle, which is going to be CV2 rectangle, and then we draw on top of the shapes one, and then we give it the start X, start Y, and then the end X and Y. And we also want to make it white. So this is the white BGR. and -1 is filled. And if the numbers are confusing you, you can just write cv2 dot filled, and it's going to be the same thing. If you hover over it, you're going to see that it's an int, which is going to be -1. So we're going to have an output frame, which is going to be the frame.copy. And we have going to set an alpha, which is going to be 0.5. So it's going to be 50% transparent. Then we are going to set a mask, which is going to be shapes as type bool. So anything that is a 0, so it doesn't have a rectangle, so it's going to have only the mask is only going to be 2 for the rectangle bits, and we are going to get the output, then the mask, only the pixels that we want to have, and we want to add it with weighted so that we can add it a little bit with a transparency factor. We want to add the frame and then the alpha, which is 0.5. We want to add the shapes, which has the rectangle. We just want to have the other transparency of the shapes. And yeah, 0 is for filled. And yeah, so and then we get the mask. Then we write output equals cv2, and then we just want to convert it, so cv3 color. BGR to RGB. You just want to convert it to an RGB format, and then we return back the output. Of course, this one draws on one frame only, so let's draw it on all frames, like define, draw, mini court, then self, and give it the frames. We then have the output frames, which is going to be for frame in frames, and we just want to have frame equal self dot draw rectangle, and give it the frame. And at the end, we just want to append it. So output frames dot append frame, and return it back. And this is it. We should now have the white box, and afterwards we should be able to draw the key points. So let's see the results till now, and then we can continue. So in the mini court, we just want to add an init.py, and this is also going to help us a little bit with exposing the function or the class outside of this folder. And we are going to go here from mini court, import mini court. We also want to have, like here, we want to initialize the mini court. So now we initialize the mini court. And now we want to draw the mini court on top of the frames. So let me do that. So draw mini court, and I will have it the output frames equal mini court draw mini court output frames. And yeah, that should be it. Let's run it and hope that it works. Okay, so we have an error. Convert meters to pixels is not defined. I think I've misspelled something, so let me check. Yeah, I've misspelled convert meters to pixels. I forgot to put the 2. So let me rerun it again. And now I have another error, which is I also wrote the uint8. So I'm going to fix it and come back to you. I think it's going to be here. And it's going to be uint8. So let me run again. So now it's working fine. We can open this up again right here. You can see that the image is a little bit weird because it's in BGR, not in RGB. But you see also the rectangle that is transparent right here. But now we need to fix the BGR one. So I see here that we also convert it to BGR to RGB. And yeah, maybe we don't need to do that. Give me a minute. Yeah, we didn't need to convert it again from BGR to RGB because it was RGB from the first place. And now we have the like the mini court background setup. Okay, so now that we have the background rectangle ready, we can just start drawing the court. So to do that, we can just write a new function right here, define draw court, which is going to take self and a frame, and we are going to loop over each point. So in range and start from 0 till the self dot drawing key points, and we loop 2 at a time. And x is going to be int the self dot drawing key points of I, and y is going to be the same but plus 1 because it's going to be the next variable. And then we just add a circle on the frame with x and y. We are also going to set the radius to 5. We are also going to set the color. And we are going to make it filled, which is -1. Now we should have the key points ready. So let me return the frame and see the results. But before seeing the results, we need to call it. So I'm going to call it right here, self dot, and give it the frame. And yeah, that should be it. So let's call it. There is something missing. Yeah. So I wrote here like the 2 here in the length. It should be outside the length. So let's run again. Okay. Let's see the output right now. So you can see the output of this is having the key points right here, right here, right here, and it looks fine, but the width or the height of the white box is not big enough. I think we can expand it a little bit. It should be fine, but yeah. We can also make it in red, like that. We can make it in red. But we can also expand the drawing rectangle height a little bit to be, for example, 500. So that it, yeah. It's running right now, so let's see the output. Now the output looks fine. We have the court, we have everything that is ready. We just want to connect the lines, and this is going to be simpler. So in the draw court function, we just want to now draw the lines. So let's call draw lines. And so for line in self.lines, what we want to do, for line in lines. So start point and it's going to be this one. It's going to be the drawing key points of line 0, and this is also going to be the y of it. And we're going to have an endpoint also, and it's going to take from 1, so line 1. So each line is going to have, like we saw, like 2 points, 0 and 1, and we want to just connect them both. And we're going to connect them both with a CV2 line, and we're going to give it the start position, the end point, and we are going to give it also a color. Let's say it's black, and yeah, that should be it. Let's run it and see the results. So I made a small mistake earlier where I didn't multiply the position by 2, and this is because the 0th position starts from 0 to 1, the first position starts from 2 and 3, and the second position starts from 4 and 5. So you can see that you take the position multiplied by 2 to get the x1 and then add 1 to get the y. So you need to do this the same here. And if you run it here, and you're gonna get the correct output. Wait for a while, and you should be done anytime soon. Okay, now it's done. If you look at it now, you have the lines ready. We just don't have the net line. This is going to be an easy one. It's just going to be the middle point of the court. So we can just calculate it real quick. And yeah, to draw the net, we just get draw net. So we need to get net start point, and it's going to be self.drawing key points of 0, because it's like the 0th position, and it's also going to be int, which is like the start key point is going to be the 0th position, which is x, which is going to be this x, and it's going to be this x at the same time, but it's going to be in between this one and this one. So let me calculate it, like get the positions of them both and then divide it by 2. So we can have self. Actually, let's use their equation, but edit this to 5. So now we can have the start position. So let's do the same for the end position. Let's copy paste it, and it right here. Put the end position and make it start from position 2 instead of 0, and keep the y the same. And lastly, we just add the line, and let's make it this color, and make it start from net start and end at net end. And yeah, we can now run it and see the results. Okay, now it's finished, and you can see the court is being drawn quite correctly, and yeah, that looks good. So let's continue with that. Before closing down this class, we basically need to add a couple more functions, and yeah, so we set a couple of variables. So let's make functions to get them. So let's get, for example, the start point of the mini court. Self, and then we're going to return back the self dot court start x self dot court end start court start y. And we can also get the width of the mini court, so we can define get width of mini court, and we can return back the drawing width. We can also return back the key points if we want, so let's get court key points. Actually, let's call it court drawing key points, and let's return the drawing key points. And yeah, I think this should be it. So now we're done with drawing the mini court, and I think we are ready to go back here and continue. So right now we have the this output, and everything looks good, but let's now detect the ball hits. So at this frame exactly, let's minimize this a little bit. At around frame between 10 to 12, the ball was hit, and we want to get this ball hit frame and know which player hit the ball, and the same here. So we can continue to detect the ball frames. So now we just want to detect the ball, we just want to detect the ball shots. So we can create a temporary folder that is called basically maybe called analysis, and let's make it a folder. Sorry about that. Let's delete it. Then let's create a folder called analysis, and inside of it let's create ball analysis.ipynb. Now let's import pickle, because we're going to read the pickle stub that we have for the tracker right there. And we are going to also import pandas. we are going to import matplotlib.pyplot, and yeah, I think that should be it. So the first thing is that we want to read the pickle file. So we are going to read it like that, and let's call it ball positions. And let's also refer to the correct path, which is called tracker stubs and ball detections dot pkl. Let's run it, and let's make sure that it threaded correctly. So it threaded correctly. We can also copy paste the filling of the interpolation that we had. So let me open up the tracker again and the ball tracker, and let's copy this code, and yeah, let's copy this code and put it right here. This is going to be for as PD. So yeah, you just run it again, and now you just have the a pandas data frame that you can plot out. So yeah, so the first thing is that we basically want to have the position of the ball, and we can make calculate the center of the ball. And the way that we do that is that we can have we can also create the mid y only, like the middle y, and it's going to be this one, like the y1 plus y2 over 2. And this is going to be get us the middle of the y. Afterwards, you can see that we have pretty smooth detections, but in some scenarios we need to remove any outliers, and we can do that by having a rolling mean. So we can add it right here. We actually don't need it here, but let's add it for other use cases. Maybe other videos have this jittery action, but we can have the rolling mean. And this rolling mean is going to need a window, so we are going to have a window of 5. And we are also going to set a minimum period of 1. And we are not going to center it, so center equal false. And we are going to get the mean. Afterwards, we can basically plot it. So we can plot this out. So when we plot it out like this, you can clearly see where the ball was hit. So the ball was moving like this, then it changed y positions here, and it then changed y positions here, it changed y positions here, it changed y positions here. And this is like the normal behavior of the ball. Like if you see that, the ball is moving in the y direction like this, and after it was hit, it changed direction. So the ball, instead of being more and more, like the y coordinates is being increased, it suddenly changed directions, and now it's decreasing till the other player starts hitting it again, and instead of decreasing the y, it starts increasing again. So we want to detect when exactly in the plot that the that this is being like the y coordinates is being changed. We can do that by like analyzing the difference between each point and the other point. Is it increasing? Is it decreasing? And how much? So we can define a delta y. So we can have the ball positions, delta y, and then we have the define ball positions rolling mean, and we get the diff. This difference is just going to subtract the two consecutive like rows from each other. And yeah, we can also try and plot it out, and it should give us approximately a very similar graph. So there you go. It's a very similar graph, and you can also understand where the ball was hit, here, 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 and here. And yeah, you can continue on with that. So yeah, to understand where the ball was hit, we are going to loop over this, and we are going to determine whether the ball is increasing or decreasing, the delta y is increasing or decreasing, and we are going to get the position of the frame number where the ball started to decrease when it was increasing, like this change, and it kept on changing for at least like 25 frames. So we will check this, and when it's at the bottom, we will check if it's increasing again. It's going to be a very simple code. So we can have the ball positions, and we can have the ball hit is all set to 0. So we can have it all set to 0 at the beginning, and then I'm going to loop over this data frame, and like this. df ball positions minus int, and I'm also going to have the minimum change frames. For hit. And I'm going to set it to 25. So at least it's moving, like increasing, and then at least for 25 frames it kept decreasing. So the change here kept decreasing 25 frames at a row, or like maybe not in a row, but within a certain buffer. So I can just have this and loop over like the length of the ball positions till minus minimum changes, and let's put a buffer of 20%. So let's multiply it by 1.2 and continue. We want to detect if there is a negative change. So there is a negative change that is happening where the ball is here and then it decreased in value. So we can have a negative position change, whereas it's going to be like ball positions delta y, iloc of iloc is just getting the like the row number I, and it's going to be, if it's a negative change, then it's going to be greater than 0, but the preceding one is going to be less than 0. So it was increasing and then it was decreasing. So now it's going to be less than 0. We also want to detect the positive change, which is, it was decreasing, and then it was increasing, and then it became increasing. And we can call it here positive change. Positive position change. And if there is a negative change or a positive change, we can begin to count how many frames the change kept on going for. So for change frame in range I plus 1 till I plus int, and then minimum, let's call it like the oh yeah, so we need to multiply this here, and let's copy this, put it right here, and we yeah, and let's add 1 to it. And for this, we will need to copy paste the same thing again. We will need to do it and detect if there is a negative change or a positive change, but let's call it change in the following frame. Okay, so now we have the change in the following frame, and yeah, but instead of checking I plus 1, we need to check the change frame. And if there is a negative change, and there is a negative change in the following position, we just change count and make it change count plus 1. I change count plus equals 1. We want to do the same thing for the positive change, so it's going to be the same thing. And at the end, we want to have if, and yeah, here we just want to have if the change count is greater than the minimum change hit minus 1, and if that's the idea, if that's the scenario, then we need to change the location, like the ball hit in the row number I to 1, so that we now have the basically the ball hit position. So let's run it. You're gonna find a couple of warning messages. Don't worry about it. And yeah, you can run it again, and you can see the ball hit column that is already there. We can filter it to only produce or to only give us the ball hits that are 1. So let's do it like this. So ball hit equals to 1. And let's run it. So you can find that there's a hit in position frame 11, frame 58, frame 95, frame 131, and frame 182. And let's check if that's correct. So here the frame number will come in handy. So let's move this and see. So approximately frame 11 starts the hit. And if we go back again here, so we have a hit in frame 11. And if we continue down the line, we can see that around frame 57, which is here 58, another hit was being done, another shot was being done. And again, right here, around frame 95, which is another hit. We can also see here, which is around 131, another hit is being done, and the last hit is at frames 182. So the logic is being, is quite good, and we can continue on from this. So we can just get those positions by just copy pasting this, then saying that we want the index of it. Okay, then we want it to make it to list. You need to remove those brackets from the index, and now you have it as a list. We can now just frame nums. You can have it frame nums with ball hits. Okay, so now it's all good. You can paste it in right here. And you can also try and finalize your code. I'm just going to copy all this, put it all right here, so that I can copy the code and paste it in the ball tracker. So we can, from here, we can start by writing the define get ball shot frames. It's going to take in the ball positions, and it is going to run this basically. So again, we need to convert this into a data frame. So we can copy this from here like that, and yeah, I think we're done. So it's having it, but it's not returning it yet. So we can return it, and now the function is done. So let's do it right here, and we can detect ball shots, and we can have the ball detector ball tracker dot what's the get ball shot frames, and we give it the ball detections. We can write here ball shot frames. Now let's print it out and see the results, if it's the same or not. So I think I forgot to copy paste something, which is initialization of the ball hit. So it's going to be ball hit, and it's going to be all zeros. So let me run it again. So yeah, right now we have the 11, 58, and 95. All the frames that we detected before are now being detected. So all now is good. We can keep printing it, but yeah, we'll remove it quite shortly. Up next is just we want to convert the player positions into the mini court positions. And this is going to help us draw the mini court. That's first. And the second thing, it's going to help us determine the amount of distance that is being covered by any object, and by tracking it on the mini court and not the actual pixels right here. So let's start by doing that. So you can go back to the mini court that we had, and we are going to add one more function, which is convert bounding boxes to actual mini court coordinates. So let me explain the logic first. We are going to measure the distance between any key point, let's say key point 2, and the player itself. And now we have the distance in pixels, but I want to measure how much, like this distance in meters. So what we have for reference is that we have the actual height of the player. So we have the height in meters, and we have the height in pixels. So we can do cross multiplications to find the distance between the second key point, or basically the closest key point, and the player position. And then I can come here and say, okay, I have the distance in meters. Can we convert it back into pixels? And we already have this function, so we can just call this function with meters, and it will draw it in the position that is going to be relative to the court. And yeah, that is going to be the whole logic of this. So let me begin the code. So we can have the convert bounding boxes to mini court coordinates. And we are going to take the player boxes, and we are going to also take the ball boxes. We're going to convert them here into one function, and for convenience. And then we are going to take the original court keypoints, so yeah, let's start first by defining the player heights. So we can say that player 1 has the constants dot player 1 height in meters. We can have the same thing done for player 2, like this. And then we can define the output player boxes. And we can define the output ball boxes. And the first thing that we want to do is we want to loop over the frame. So we're going to have the frame number, player bounding box, in enumerate, which is going to return back the index that we are looping over. And let's loop over the player bounding boxes right now. So in the player bounding boxes, there are multiple tracks, so we are going to loop over each track. So I can have the player ID, and I can also do the bounding box in player.bbbox.items, and now I have it ready. The first thing that we want to do is that we want to get the foot position of it. So the foot position is basically going to be like, we are going to get the middle of the box in terms of x, and then get the maximum y. So it's going to be right here. We don't want to have it in the middle, because here is actually where the player is standing. It's not here, it's actually here. So to do that, we can go back to the utils and add another function in the bbbox utils. It's going to be called get foot position. So we can have the get foot position, and it takes in a bounding box and it returns in the foot position. So we can do it like that. So x1 plus x2, which is the x and we can divide it by 2. And we return also the maximum key point. We also want to expose it in the init, and we want to import it. So we can get the foot position, of the BB box, and this is the foot position. Okay. Now I want to get the closest key point. So I want to measure we want to get the closest key point in pixels, basically. And we don't have to search all the key points. We can limit it to a couple. So let's choose them right now. So you have this 0, which is going to represent the end. And we have the 2 is going to represent the other end. And let's also take the middle of the course, which is going to be 12 and 13. This is going to be fair enough. Let's not overdo it and search all key points. So let's search only 0 and 2, which is the extremes, and 2 middle points, which is 12 and 13. This one and this one. Yeah, so we will need to have a function get closest key point index that basically takes in the foot position and the original key points and the filtered, like the key points that we want to search. We said 0, 2, and 12 and 13. And we return back to the closest key point index. And this closest key point we will be using to measure the distance between it and the player. And yeah, it's going to be the point of reference for us. So let's also add this get closest key point index to the BB box utils. So we can have it right here, get closest key point index, and we can have the point that we want to measure the distance from. We can also get the key points and the key point indices that we want to have. And yeah, we can loop over them. Let's remove the suggested code, and we can get the closest distance, which is going to be float of infinity right now, and we can get the key point index, which is going to be key point candidates of 0. We're just going to take the candidate 0 right now and overwrite it when we loop. Then we are going to loop over the key point candidates indices. So let's call it index in key point indices, and let's remove also the suggested code. I don't think that it's going to work for us. So we can write that the key point is equal to key points of key point index times 2. And then we want to also have it for the y. So it's going to be the same, but plus 1 at the end. Then we are going to measure the distance, which is going to be only in y distance, so let's only measure y distance. So 0.1 minus key point 1. And if distance is smaller than the closest key point, then what we do is that we assign the closest, we assign the distance to the closest key point, and then we have the new index that we want, and at the end we can just return it. Let's now expose this function to the inits again, so we can access it. Let's go back to the bounding box, to the mini court, and we add also this function. And let's also, so it's already being utilized right here. Then we want to get the player height in pixels. So let's get the player height in pixels. I want to also show you something before we get the player height, is that the player might be lunging and is not straight up like this one and this one. So the idea is that I'm going to get the maximum height within a 50 frame to ensure that the pixels truly represent the total height of the player. So let me try and get the frames that we are going to search for. So let's get the frame index minimum, and it's going to be the maximum of 0 and frame number minus 20. So we're going to we're going to go back 20 frames, and we want to also have the maximum number, the maximum index, which is either going to be the length of the frames or frame number plus 50. So we can go up to 50 frames. Then we want to detect the height of the box in pixels. So we can go back to the utils and add another function to that. So we can have define get height of BB box, and it basically takes a bounding box. And let's see the return, and it returns back the height, which is the maximum y minus the minimum y. We can also expose it right here, and we can import it here, and we can simply get the heights of this. So we can say BB boxes heights in pixels, and we can simply have like for I in range, and it's going to be frame minimum till frame maximum, and we are going to get the height of the bounding box, and this is going to be player bounding box of I. Now we have a list of heights of bounding boxes in the frames in the list frames that we want. We want to get the maximum one, so we can say max player height in pixels, and we can get the maximum bounding box height. Afterwards, we want to get the court position. So now we have enough information to convert this into the court position that we want. So let's create another function that is called get mini court position. So we are going to define another function. So get mini court coordinates. It's going to take in the object position, it's going to take in the closest key point, and it's going to also take the closest key point index, and it's also going to take the player height in pixels, and let me just organize it into different lines so that it can be easily seen. And so player height in pixels, and then player height in meters. So player, we can copy this and say meters. Yeah, so right now we have the closest key point index. Let's also define the, let's get the actual point. So we can say closest key point equal, so it's going to be the original key point to the closest key point and then multiplied by 2, and we are also going to get the y position of it. Okay, so sounds good. Now we want to continue with the mini court coordinates. We want to first get the distance between, like the distance x and the distance y between the closest key point and the player. So we can get it. So we can say distance from key point x pixels. Then we can say distance from key point y pixels. And then we can say it's equal to measure xy distance, and you give it 2 points, which is object position and closest key point. Object position and closest key points. Now we don't have this function yet, so we can go back to the bounding box utils. We can basically define it and see it right here. Like now we get the x position, the x difference, and then the y difference separately. And when we return them both, we also want to expose it in the init, and we also want to import it right here. And after we get this, we want to convert this distance into meters. So let's convert pixel distance to meters. And what we do is that we write distance from key point x in meters equal convert pixel distance to meters, and then we give it the pixels, and we also give it the player height in meters and then the player height in pixels. So player height in meters right here and player height in pixels. We want to do the same thing but for the y position. So let's copy paste it and get it also for the y position. Like that. And now we have the meters ready. So this is the amount of meters that the player has really moved, and now we this is the amount of meters that is between the key point and the player. And now we just want to convert this into pixel coordinates again, but for the mini court. So it's going to be for the mini size court. So we are going to say the convert to mini court coordinates. And what we do is that we write mini court x distance in pixels self dot, we have a ready-made function for that, which is convert meters to pixels, and we just give it the meters. So like that. We do the same thing for the y coordinates like this. We change it here to the y, and we change here also y. And yeah, we also can get the closest mini court position, the closest mini court point, key point. It's going to have the same order as the original key points, so we don't have to do any calculations here. We just need to get the position of it. So we can say closest mini court key point is equal to self dot drawing key points of closest key point index times 2. And we also want to have this for the y, but we are going to add 1 because it's a y position. And yeah, that is it. Let me just format the bracket correctly. And at the end, we just want to add the distance in pixels to the mini court position to have the last position. So it's going to be mini court player position is equal to mini court player position of 0 times the distance in x, and we want to have the same thing for the y. And yeah, that is it. We can return back the results like that, and yeah, we can now call it here. So we can call mini court player position which is going to be calling get mini court, and we give it the foot position, and then we give it the closest key point, then we give it the closest key point index, then we give it the height in pixels of the player, and we also give it the player height in meters. We then want to assign this. So what we want to do is we want to have an output dictionary for each frame. So an output player BB boxes dict, and it's going to have the player ID as the key as usual, and is going to have the position as the value. Now we want to do the same thing but for the ball. And since the ball doesn't have an exact height, or the height of it is going to be very small, we are going to use the closest player to the ball, and we are going to do the same calculation for it. So let's calculate the balls first. So let's get the ball box, which is equal to ball boxes of frame number, and then we have the ball position, and we are going to get the center of the box. Let's not get the foot of it right now, but let's get the center of it, and we can get the center of the box, and we can call it off BB box. We can go here, we can define get center of the BB box, and we can return and write it right here. So this is going to get the center of the box, which is going to get both x's and divide them by 2, get both y's and divide them by 2, and this is going to get the center of the box. Then we also add it in the init. We also import it here in the mini-court position, and now we can utilize it here. So now we have the ball position. We can get the closest player ID to the ball. Closest player ID to ball, and this is going to be the minimum of the player BB box dot keys, where actually it did it quite good. So this is what we do. Measure distance, I think we already have the measure distance in the utils right now, so we don't need to rewrite it. So let me explain what the suggested code was all about. So right now it's going to measure the distance between the ball position and the get foot position. Let's also get the center of it. Let's get the center position and the center position of the player. So it's going to measure the distance between this and this, and it's it's going to return the key of the minimum player bounding box. And yeah, so that is it. So we can go here and we can go here and we can write the code for the ball, which is if the closest player ID to the ball is equal to the player ID, what we want to do is to get the closest key point also. So closest, let's copy paste it. So we need to get the closest key point again, like that. And instead of using the foot position, we're going to use the ball position. And now we can just run the mini-court function again, like this. And instead also of the foot position, we write the ball position. And now we have those two in place, and the maximum height and the player height are also being put. Now the last thing is that we want to have an output dictionary. So let's call it output ball BB box. So yeah, let's just add the output to the to our list, which is going to be output ball boxes dot append, and it's going to be 1 because it's only one ball, and we're going to get the mini court position right here. And at the end we want to return both return the output player dictionary and the output balls. Actually, we don't want to return the we don't want to return that. We don't want to return the dictionary. We want to return the output player boxes for the whole frames. So let's add it right here. And let's replace it here. So now we are ready. So this is the coordinates of the mini court for the players and the balls. So we can go back to the main and we can call it from there. Right here, we are going to convert the positions to mini-court positions. So we are going to write player mini-court detections, and we are also going to write ball mini-court detections. And those are going to be equal to mini-court dot convert to mini-court positions, and we give it the court points, and so we give it the player detections and the ball detections and the court key points. So we need to also give it the court key points right here, like that. And yeah. Now we want to basically display this on the mini court, so we can have actually let's run it first, make sure that nothing crashes, and then we can create another function that draws those positions onto the mini court itself. Okay, so we have a small error. I'm going to trace it back and come back to you. So the problem was that I renamed the function here. It was convert to mini-court positions. It should be convert bounding boxes to mini-court coordinates. So let me run it again and see if we have any more errors. Okay, we have one more error, which is in line 32 of get center of the box. And I think the box has a key 0 error. So let me trace it back and come back to you. So I had two problems in the code. One is that I was treating this as a bounding box, ball bounding box, but it was actually a dictionary. So I needed to get the one track, the track number 1. And this will be now a bounding box. And the other one is going to be the this one. I was giving it a dictionary. I needed to filter out the current player ID, and this is how I did it. And yeah, that is now a bounding box also. So if you can rerun it again, it should be working fine right now. So now it's working fine. But we want to also see the results. So we're going to make another function that is going to add these drawings to it. And we are almost finalized with this mini court, so bear with me a little bit. So to draw any points on the mini court, we can just call draw points on mini court. And we can write the self, we can get the frames, and we can get the positions that we want to write it on. And we can also specify a color. We can give it a default color. And we can loop over the frames, frame number, and frame in enumerate frames. We can also loop over the positions that we want to output. So right now we have the position of this frame number. We have the player ID. We don't need it, so we can remove this. We have the position, and we can draw a circle with the frame and the position, and then the radius, the color, and its filled. Just to make sure that the position is ints, we can just write it like this, position, and we can make it as ints like that and like that, just to make sure that those are ints actually. And yeah, x and y. So we can call this on our code. So right here, we can have the output frames equal mini-court dot and then draw points on mini-court, and then we give it the output frames. We also give it the positions that we want to put, which is the player mini-court detections. Player mini-court detections. And we can do the same for the balls. So we can call the ball mini-court detections. And we can give it another color just to differentiate both of them. And color is equal to 0, 255, and then 255. That's another color. We can then run it. Okay, we have another error, so let me trace it back and come back to you guys. So yeah, we didn't return back the frames, so we can just return it back here, return frames, and it should work fine. So let's open the output, and we don't see the key points yet. We don't see those the players yet on the here. Let me trace it back and come back to you. So if you were following along, I made a small mistake with the brackets. Right here in the closest mini-court key points, I did the +1 outside the bracket. It should be inside. So this was the problem. So you can save it and you can rerun it again. And you should find that the output has been on your output video. Just wait for it a little bit, and yeah, that is it. So you can open this here, and you can see how the player is relative to the position here, and the other player is here, and the ball is also very close to its position. And if you run it, you're gonna see that the ball is moving quite correctly, and the ball is quite that the people is moving correctly, and the ball is a little bit jumpy because it's fast. But otherwise, everything looks good, and we can proceed from here. So the last thing that we are going to work on is going to be the output of the kilometers per hour. And I'm going to show you the output, the final output again. And this is it. That is the last thing that we are going to work on. It's going to have the shot speed and the player speed, and it's going to also like count how many shots that the player has shot. Each player has shot, and I'm not displaying it here, but we'll be calculating also. So let's dive right in. This is the last bit, but afterwards you're gonna have a super cool portfolio project to add to your CV, so it's going to be totally worth it. Yeah, so let's jump into the main, and I think we are not gonna need any other classes. Maybe I'm wrong, but I think we're done with those. And the way that we are going to do it is that we are going to loop over each shot in those frames. And let me go through the logic first. So we are going to go each shot in the frame. So we have this, this frame number, which is frame number 11 for this shot. And we have the other shot, which is this one, which is frame 55. We are going to measure the distance that the ball has covered. We are going to measure it in pixels first, maybe in the mini court, and we can then switch it to meters. And we also have the frame difference. So we know that this frame is frame number 11, and it took it around till frame 55, which is around maybe 40 something frames to go there. And we know that per second we have 24 frames, so we can measure the time in seconds, and we have the meters, so we can measure the speed, which is the kilometers per hour. We also have, like, this is the player who shot the ball. We also have the position of the opponent player and the amount that he covered, the amount of meters that he covered. And we also have the time that he covered it in. So we can also measure the player speed. So we are going to loop over the shot and take the next shot into consideration and measure the distance covered by the opponent player and the ball, and basically calculate the kilometers per hour from here. So let's start. So for the shots, we are going to loop over the shot, which is going to be shot index in range length, and we are going to have it shot frames, which we got earlier. And we are not going to include the last one, because the last one doesn't have another one that is going to be like another frame, so we can't measure the exact distance covered or the amount of time covered, but we are going to measure it for all other ball shots. And yeah, we can get the start frame, basically, which is going to be the ball shot, and we are going to get the ball shot index. This is the start frame, and the end frame of the shot is going to be the next ball shot. So it's going to be ball shot index plus 1. We can get the time difference in seconds of the ball shot, which is going to be ball shot time in seconds, which is just going to be the end frame minus start frame over 24, because we have 24 frames per second. Then we have the get distance covered by the ball. And first we want to measure the distance in pixels. So what we do is that we get the distance covered by ball in pixels, and we are going to measure the distance. We have this function in the utils. I don't know if we imported it here or not, so I don't think that we did. So let's do that here. And yeah, so let's continue on. And so we have the measure distance function, and it will take the ball mini-court detections of start frame, and it's going to take the ball mini-court detections of the end frame. And because we only have one track, so then we are going to just get the one. Yeah, so we can use the convert pixels to meters that we have in the mini court, and it should return back the meters. And now to measure the speed, so speed of the ball shot in kilometers per hour. We have the speed of the ball, which is going to be the distance covered by ball in meters over the time in seconds times 3.6, and this times 3.6 is just going to convert it to kilometers per hour. Now this is going to be the speed of the ball. Now we want to get the speed of the opponent player, so we can have the opponent player. We can have the opponent player speed, and before that we can also have the but before that we need to understand which player shot the ball. So we can do that by simply measuring the distance between the ball and the two players, and getting the player that is closest to the ball when the ball was shot. So we can do that by simply doing the player who shot the ball. We want to do that. So player, we want to get the player positions and the player mini-court detections of the start frame. Let's get the player that is closest to the ball. So we can get the player who shot the ball, which is going to be minimum of player positions dot keys, and we are going to have the lambda player ID, and we are going to measure the distance. And the distance we are going to measure it is between the player position and the ball position. So we have the player positions of player ID, and we also have the ball detections of start frame of 1. And this is going to return back the player ID with the minimum distance. With that in hand, we can also know which player ID is the opponent, which is going to be player's opponent player ID is going to be opponent player ID. 1 is going to be 1 if the player shot the ball is equal to 0, and else it's going to be actually it's going to be 1 if it's 2, and else it's going to be 2. So let's say that the player who shot the ball is player 2. I'm going to return 1 as in the opponent player. I'm just going to return the inverse of it, and if it's not 2, then I'm going to return 2. That's the opponent player. I want to measure the distance covered by the opponent in pixels. So distance, just like what we did in the ball, but we are going to do it for the covered by the opponent player. By opponent in pixels. And it's going to measure the distance between the player. It's going to player like the start frame of the opponent ID and the end frame of it. So that is good. Now we want to convert it into meters. So that is also going to be the same as the mini-quart one. And then we want to measure the speed. So speed of opponent, which is equal to the distance covered by opponent over a ball shot time frames in second, which is going to be the same frame times 3.6 to make it in kilometers per hour. Yeah, so now we have the speeds and we have the speed of the ball and the speed of the opponent. We just need to put it in a type of a data structure, so that we can display it in a better way. So I am going to choose to display it in a list of dictionary because it's going to be easier for me to change it to a pandas data frame and to expand it to the whole other frames as well. So let's create this data structure, which is going to be just a list of dictionary, stats, data. It's going to have a list, and this list is going to be a dictionary. The first one is going to be a dictionary. It's going to have a frame number, which is going to be 0 at the beginning. Then it's going to have the player 1, number of shots, which is going to be 0. Then it's going to have the player 1 total shot speeds. Now this now the number of shots is the number of times that the player have shot the ball. The total speed is the summation of all the speeds that the user have done. And you can calculate the average by just having this over this, like this number over this number, you can get the average. So I'm not going to have the average right here, but I'm going to calculate it later. And we can have the player 1 last shot speed. So this is the latest shot that he did. What's the speed of it? And we can also do it with 0. And we can have the player 1 total distance, total player speed. So total player speed, which is going to be 0. And we can also have the, last player speed. We can also have the last player speed on. And we can do the same thing for the player 2. So number of shots and the total speed of the shot, the last shot, the player speed, the last player speed as well. So that should be it. So let us import a copy mechanism, which is from copy import deep copy, because in order to copy a dictionary, you need to copy it and not copy its reference. So deep copy helps us to copy the values. And the way that we're going to do that is that at the end of this, we are going to create a status, like the stats, the statistics. So we have the current player stats, which is going to be a deep copy of the previous player stats, and we are going to overwrite some things. So, for example, the frame number is going to be the start of the frame number. And then we want to have the player number of shots, which is going to be player number of shots plus 1. We want to also have the total speed to be added. We also want to have the last shot to be added here. and we want to add the opponent player. So the current opponent player, which is right here, we want to add to the total speed of it, and we want to add the last speed. And afterwards, we want to have the player stats data.append current player stats. So now we have, for each start frame, we have this dictionary again, but with the new stats. And for that, we will need now we just have the the shot frames, and we want to expand it to the whole list of frames, so that we just can loop over without too much logic. And basically from frame 0 to the first start frame, we just want to duplicate this again and again, so that we have so that for each frame we have its statistics. We can also loop over it and do some logic so that we can know which position to choose from here. But I'm going to choose to duplicate it and to make it into a pandas data frame so that it can be easier to display. So let me change it into first the data frame, so data.df. I don't know if we have pandas already here, so I think we do, maybe we don't. And then we have it. So let's import pandas. Now we have it as a data frame. Let's also have a frames number data frame. So frames df, which is going to be pd data frame, which is equals to frame number, and it's going to have a list of range of length of the video. This is going to be a data frame with frame number, and it's going to have 0 till the length of the frame number. I think there's a bracket missing or something like that. Let me figure it out. Yep, there was a bracket missing. And I just added it right here. And now we can just do this and merge it. So now we are merging the frames data frame with the player stats, and I'm going to have it a left join on the frame number, and that is going to result in multiple rows going to have nans, because only the start frames of the ball shots have values, so other things will have nans. And I want to fill it, so the way that I'm going to do it is that I'm going to do a front fill, and basically like this, which is equal to ff fill. It's going to replace a nan with its previous value that is not a nan, and do this so on and so forth, so that every frame we have the output of it. Now I want to basically calculate the average of it. So let's calculate also the player stats and data df of player average shot speed. And we are going to divide the total over the number of shots. I think I misspelled it right here, so let's do this, and player 1 shot speed over the number of shots. This is the correct one. It should be player 1 average shot speed, and let me check this, player 1 total shot speed and the player 1 number of shots. That looks correct. Let's do the same thing for player 2. And let's do the same for the player speed. So this is the player speed, and it's also getting the total over the, it's not doing the over correctly. So it should get the other. So it should have the total speed over the opponent's number of shots, because the player should only, like, we are only calculating the run when a user shoots and how the opponent reacts to it. So this is the player 1 over the number of shots that were done over player 2, and we're going to do the same for player 2. And we're going to get the total of player 2 over the number of shots done by player 1. So now all the statistics are done. We are just missing the last drawing of this. So we need to draw those stats, and yeah, and we are done. We are good to go. So in the utils, we can do another function, another file called player stats drawer utils.py, and we are going to put the drawing logic here. It's not going to be logic, it's just going to be drawing. It's going to be easy to do, but it's going to consume a lot of lines, so I thought to put it in the utils and not in the main, just to keep the main clean. So we have the numpy as np, and we also want to import cb2, and let's define the function. So the function is going to be draw player stats, and we are going to have the output video frames, and we are going to have the player stats, and we are going to loop over it. So loop over the player stats. So in player stats dot iter rows, and we have the player 1 shot speed as in row of player 1 last shot speed. We have also player 2 shot speed, that is going to be last player 2 shot speed. We want to have the player 1 speed, which is going to be player 1 last player speed, and we want to have it also for player 2. We want to also get the average player speeds, so average 1 player shot speed, and then the player 2. We want to do it for the speed also, and average player speed. Now we want to get the frame, so frame is equal to the output frame of index, should be index. And now we want to have, basically, it's not that one, we want to have a black transparent box, so we're going to add also the position of the box and then make it transparent, and then we're going to add those statistics. So adding those statistics are going to be, we are going to need the shapes again, because we're adding a transparent black box, which is going to be also zeros, like the one that we did above it. And we want 0 like frame, and we want to also have it u int 8. Let's write it correctly this time. And then we have the width is equal to 350. The height is equal to 230. We also want to define a start and an end x. So start x is going to be frame.shape of 1 minus 400. And we also want to have the start y, which is going to be of 0. And I think I wrote shape wrong, so let me fix it. And 550. And let's also define the x's. So we have the end x is going to be start x plus width, and then end y is going to be start y plus the height. Then we are going to have the overlay, which is going to be this one. It's going to be the overlay start x, start y, and x and y. And we are going to put a black one this time, a black box this time, and it's going to be filled. And we are going to define an alpha of also 0.5. So we are going to add it weighted again, and we're going to add it overlay, the alpha, the frame, and then we have the rest of it. Then the output video frames. Then we can just have the output video frame of index is equal to the overlay, is equal to the frame, sorry. Okay, now it's time to put in the text. Now the text is going to be just putting the text, like the times that we put the text here before. It's just going to be a matter of choosing the positions. So I'm just going to copy paste it and walk you through it. So I copy pasted it right here, and right now we have the player 1, player 2, and then I put the text. I chose the start position and the end, and the start x and x. I also chose the colors. I did the same thing. I put the shot speed. I then wrote the shot speed themselves, and then I did the same for the player speeds, and then I did the same for the average speeds. So currently right now, what I want to do is export this, is expose this again. So from dot player stats import draw player stats. We want to also import it in the main right here, like this, and we want to now draw it. So let's draw player stats, and we can have this like this. So we can have it like this. Draw the call the draw player stats function, and now we just run it. So there's an error here that is called convert pixels to meters, because the minicord function does not have convert pixels to meters. It has convert meters to pixels. So we will need to import that from the utils, convert meters to pixels, and we also want to import the constants. So what we do here is that we just want to convert it and use the double line width, like the width of the field in meters, and we also have the width of the minicourt. So we are going to use those to do to convert the pixels, done into meters. So what we're going to do is that we are going to do like this. We're going to choose the meters right here. Then we are going to give it the reference, meters, which is going to be constant.double. Whoops, it's not that. It was filled incorrectly. So you have the width, and then you have the minicourt, and then you can get width of the minicourt. Get minicourt height. I think I need the width of it. Let me go and check if there's the width ready. This function, get minicourt, get width of minicourt. I think we have this function. So yeah, so we have the get width of minicourt, and we will do it again right here. And instead of that, we can use this and just delete that. Let's run it again. So player 1 last shot speed. I think this one is in the drawer, because I added another S. I think there shouldn't be an S like here. But let me check the line 139, which is, yeah, so it's going to be the drawer. So yeah, the speed is going to be speed, not speeds. So like this. So let me run it again. And now it's done. So you can go back to the output and see it. So there is a little bit of overlap, so you can actually push it down a little bit. So let's do that. Let's move this here. So let's move it down like 50 pixels. So let's make it start at 50. 500, not 550. Let's also specify the width to be a little bit more. I think it's going above. No, it's not. Oh yeah, because it's not. So you're gonna find it to have. There's some weird numbers going on. So we have some weird numbers like here, like 1,000 kilometers per hour, and here is also 1,000 kilometers per hour. Let me trace it back and come back to you, but let's first, before tracing it back, let's see if this would push it down a little bit more, like 500, make it 500 instead of 550. And let's see if there's something else that breaks, but it shouldn't. Let's cross our fingers, and we should be able to see the box, but we should still be seeing some weird kilometers per hour that we need to fix. So yeah, so right now it's actually good, but the kilometers per hour is way too much, and I'm going to trace back Y and come back to you. So give me a minute. So I'm back and I know the error. I've used the convert pixels to this. I've used convert this meters to pixels, and I should have used the convert pixels to meters. So I have the distance covered in pixels and I want to convert it to meters, but I used the wrong function, and you should be using this one, convert pixel distance to meters. And if you run it again, you should be able to get the correct output. So you can now see, as soon as the player hit the ball, you can see the shot speed of the player. Like this is 33 kilometers per hour, and player 2 is going to move by 1.7 kilometers per hour. And when the other player shot, you can see that it was a harder shot by 43 kilometers per hour. And the other player moved with 4.5 kilometers per hour. And if you see that, this player sprinted actually, so you can see that it has a 9 kilometers per hour. And yeah, you can also see the averages right here, the average player speed, the average player shot speed, and the actual player speed. You can do all sorts of fancy stuff like the number of shots, and you can analyze how fast a player is running when he's losing the ball, and you can analyze how fast the ball, how fast the ball is shot to make a winning shot. You can also do a lot of other stuff like check whether the ball is inside or outside the court when it hits the ground. And the project can be very big. I chose to make it simple right now, but yeah, we didn't also do anything with the net, so you can also add a little bit of net logic if something goes wrong or hits before the net. So yeah, you can build on this, but currently you have a very cool portfolio project right in your belt. And hopefully it's going to help you land a job in computer vision and AI. So that's it, and have a wonderful day.